You are braver than you believe. You are braver than you believe. Stronger than you seem. And smarter than you think. So, hello, my shimmering stars. I, Shaurya, is going to start one short video lecture on chapter hydrocarbons. Students, in our victory batch, we have already covered IUPAC, isomerism, and GOC. Now we are going to start the most important chapter, that is hydrocarbons. So get ready with your books and let us start this chapter. First of all, students, the one thing that arises in our mind is what are hydrocarbons? To understand hydrocarbons, let us recall about organic chemistry. If I go to define what is an organic chemistry, so you would say that organic chemistry is a branch. It is a branch of science. It is a branch of chemistry in which we deal or which we study with the hydrocarbons and its derivatives. So what I am saying, it is the branch in which we study about hydrocarbons and its derivatives. Now, students, question arises, what are hydrocarbons? Hydrocarbons are those organic compounds that are made up of carbon and hydrogen. Okay, now we got to know what are hydrocarbons, ma'am, but what do you mean by derivatives? Derivatives are the one that we derive from something. If I am saying hydrocarbons and derivative, that refers to that we are making organic compounds from carbon and hydrogen, as well as with the help of them, we are also deriving other compounds. For example, if I talk about the simplest organic compound, simplest hydrocarbon, I would say, it would be methane, that is CH4. I'm talking about the simplest hydrocarbon, that is methane, which is CH4. Why it is the simplest hydrocarbon? Because it contains only one carbon in it, right? Now, students, what I will say that kindly remove one hydrogen from here. So if you are going to remove one hydrogen and you are going to add another group here, for example, you are adding alcohol, you are adding halogen group, or you are adding an alkyl group also. So what you are going to obtain? You are going to obtain some more organic compounds. So that means from any hydrocarbon, you can further derive another hydrocarbons, or you can further derive organic compounds. They are referred to as the derivatives, right? So hydrocarbons are basically what? If you want to mention, you can kindly write here. They are made up of carbon plus hydrogen, right? The compounds which have both of these, carbon as well as hydrogen. Like example is methane in front of you. Now, if I take one more example, let us see C2H6 now. How is C2H6 obtained? C2H6 is basically ethane. It contains two carbons in it, so it is ethane. We have already started in the IUPAC nomenclature. Whenever we are having one carbon, the word root is known as meth. Whenever we are having two carbons, the word root is known as eth. Likewise, we move on eth, prop, bute, pent, hex in these ways, like putting the value of n as 1, 2, 3, 4, 5, putting the values of number of carbons, and we find out word root, right? So here what I'm going to tell you, I'm giving you some of the examples of hydrocarbons. Now, students, coming to our topic today, we know that hydrocarbons are classified into basically two subcategories. One are saturated one, another one are unsaturated one. Now, ma'am, what do we need to study in this chapter? We need to study saturated hydrocarbons in detail and unsaturated hydrocarbons in detail. Likewise, if I say, if I'm going to classify hydrocarbons into two basic subcategories, number first is saturated hydrocarbons. And if I talk about second category, it is unsaturated hydrocarbons. Now students, what are saturated one and unsaturated one? The question arises. Saturated hydrocarbons are the one which contain single bond between the carbon atoms. If I say carbon contains single bond, they are referred to as saturated hydrocarbons. But if I talk about unsaturated hydrocarbons, these are the ones which contain either double bond between the carbon atom or triple bond between the carbon atom, right? So these are what? These are unsaturated one. So when I talk about single bond, I would say that these are referred to as alkanes. These are referred to as alkanes. And whenever students I am talking about unsaturated one, whenever I'm talking about unsaturated one, we have double bond as well as triple bond with us. So the double bond ones are known as alkenes and the triple ones are known as alkynes. They are known as alkynes. So students, now moving to what do we observe in alkanes, alkenes and alkynes? If I make a compound of alkanes, the simplest compound of alkane, that is the methane molecule in which there is only one carbon atom. So I would say this is CH4, this is methane. If I'm going to write it just like this, so what are you observing here? You are observing that there is a single bond between carbon and hydrogen. And whenever there is a single bond, it is referred to as sigma bond. It is referred to as sigma bond, right? All these bonds are what? All these bonds are sigma bond. Right? Now, if I talk about alkenes and alkynes, let us see one example over here. In this example, students, what do you observe? We observe that basically this bond is sigma bond because it is single bond. Okay, this bond is sigma bond because it is single bond. This bond is sigma bond because it is single bond. But students, look here. The second bond is pi bond. The second bond is pi bond. Every first bond is sigma bond. Second or third bond are pi bonds. Okay, in double bond case, second bond is pi bond. In triple bond case, second and third both are pi bonds. Now, if I talk about the alkyne structures, alkyne is basically like this. Okay, now students, if I see in alkyne's case, first bond is known as sigma bond, while the other two, remaining two are referred to as what? The remaining two are referred to as pi bonds. Okay, now students, these are the ones, these three examples are the one that are of aliphatic, that means of chains, I would say, straight chain or open chain compounds. There are some organic compounds that are aromatic in nature, which are basically cyclic. Now, what are the aromatic ones, or I would say cyclic ones? If we say these are further classified into open chain and closed chain. So open chain I've already shown you, in which the first carbon atom is not attached with the last carbon atom. That is open chain compound. In closed chain compound, the first carbon atom is attached with the last carbon atom. So if I take example of an alkane, let us take an example of alkane over here. So it is carbon, 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 carbon. Keeping the valency of carbon in mind, I am making bonds with hydrogen. Now this compound is basically what? This compound is basically the cyclic compound. It is basically the cyclic alkane. Right students, here you can see there are single bonds present in between them, in between the carbon atoms. So these are referred to as what? These are referred to as alkanes. So alkanes are the one in which we are going to observe single bond, right? Alkenes are the one in which we are going to observe double bond, and alkynes are the one where we are going to observe triple bond. If I take one example of this cyclic over here, let us take one example of alkynes. Okay, now this is the cyclic one over here. You can see there is that first carbon atom is attached. First carbon atom is attached with the last carbon atom. If this is first, this is second, this is third, this is fourth. First is attached with fourth, then it forms a ring-like structure or a cyclic structure. So this comes under the category of what? Cyclic chain-like structure, right? Now students, this was the basic that we studied in the IUPAC, or we studied in the isomerism during the classification of hydrocarbons. But now we are going to start our chapter, that is That is about hydrocarbons, in which we are going to start with what? Alkanes. Now, what are alkanes? First of all, we have studied this very carefully, but I want you all to write some of the features. Okay, to write here some of the features of alkanes, some general characteristics of alkanes. So alkanes are the ones, students, in which we observe single bonds. So they are referred to as saturated hydrocarbons. They are saturated hydrocarbons. Okay. Now if I talk over here that during the formation, now we are going to see the methods of preparation of alkanes in the coming section. What we need to know here is, whenever you are making some of the alkanes, like you are making methane, ethane, propane, so do they have a general formula? Yes, every homologous series have a general formula. So if I talk about alkanes, they have a general formula. They have a general formula. The general formula, students, for alkanes is CnH2n plus 2. This is the general formula for the case of alkanes that you need to keep in your mind, students. Other than this, students, what are the points here? If you keep the value of n as 1, what you are going to get? C1H2 into 1 plus 2, that comes out to be CH4, which is referred to as what? Methane. Why methane? Because here is one carbon atom and all of them contain single bonds, so ane will come at the end. For alkane, we write suffix as ane, right? So what we are going to get over here? We are going to get over here as methane. Okay. Now if I talk about n is equals to 2, students, what I'm going to get? C2H2 into 2 plus 2. Kindly write the value of n over here and start making all these, right? So here you are going to get what? Here you are going to get C2H6. That is going to be what? Ethane. Now coming towards n is equals to 3, what we are going to get? C3H3 into 2 plus 2, that is going to be C3H8. That is going to be propane. That is going to be propane. Now let us take one more case. N value as a 4, so C4H4 into 2 plus 2, that is C4H10. That comes out to be what? Butane. And so on you can write. N is equals to 5, N is equals to 6, you can do that structures, right? Now students, what I want you all to understand over here, that these all are basically what? These all are basically a homologous series. Homologous series. Now what do you mean by homologous series? This I have already told you in the IUPAC section, that homologous series basically differ by, the consecutive members of the homologous series differ by CH2 group. Let us see over here. If I talk about methane and ethane, both of the formulas are written in front of you. Molecular formulas are given to you. What is the difference between both of these? There is a difference of one carbon atom and two hydrogen. That is the CH2 group. So yes, if you see any of the consecutive members of the homologous series, you are going to get the gap of CH2. That means it lies in the category of homologous series. Other than this, homologous series contains the members of the same family, I would say. All of these contain single bond between them. So all of these are alkanes, hence they are a homologous series, right? Now students, other than this, what are alkanes known as? Alkanes are called as paraffins. What are alkanes called? Alkanes are called as Alkanes are also called paraffins. Now what do you mean by paraffins, students? If I divide paraffins into two categories, para refers to as little, and if I talk about affins, that means affinity. Affinity refers to the capability or to make a bond, right? So these are also known as paraffins, that you need to keep in your mind, students. Now students, other than this, what we need to know is that alkanes are basically inert at room temperature and normal conditions. Now if I talk about the simplest alkane, that is the methane, right? If I talk about methane, how does it looks like? It is C, it has hydrogen over here, it has one hydrogen over here, right? And one hydrogen over here. Now what is this? Let me tell you. Let me tell you in detail. Here, students, what you need to know is that two hydrogens are in plane. One hydrogen is towards the observer and one hydrogen is away from the observer. The hydrogen that is towards the observer, that means you who are watching this video, right? So this hydrogen is towards you, which is represented by the wedge bond. And if I talk about this hydrogen, that is away from you, that is at the back side of mine. So that is away from the observer. That means the person who is looking at the methane molecule, it is away from that. And these two are in the same plane. Now, what you want to know here, what you have to learn over here is the hybridization of carbon. First of all, carbon is making 4 bonds, hence the hybridization over here is sp3 hybridized. Right, students? And the angle here, angle basically here is 109.5 degree. If I talk about bond angle over here, it is 109.5 degrees, students. These are the basic things that you need to keep in your mind. Other than this, what is the shape here? Tetrahedral shape is there. Which shape? Tetrahedral. So this was the basic that you need to keep in your mind about alkanes, students. Now moving forward towards our main topic, that is methods of preparation of alkanes. Kindly put a star mark over here because it is going to be most important topic for you. Okay, this is going to be most important topic for you, methods of preparation of alkane. Now, whenever I am talking about methods of preparation, the very first methods that come in our mind is hydrogenation of unsaturated hydrocarbons. What? Number first is hydrogenation of unsaturated hydrocarbons. Now, students, as the name suggests, look at the name very carefully. Okay, look at the name very carefully. Here you have hydrogenation. If you are going to split hydrogenation into two parts, you have hydrogenation, where hydro refers to as hydrogen and genation refers to as addition. That means addition of hydrogen. Now, where to add hydrogen? Where to add? To unsaturated hydrocarbon. Addition of hydrogen in unsaturated hydrocarbon. Okay. Now, students, you got to know about hydrogenation. You know what is unsaturated. Unsaturated refers to as the double bond ones or the triple bond ones, right? And hydrocarbon refers to as the organic compounds that are made of carbon and hydrogen, right? Now, students, to start with the hydrogenation, first of all, you need to keep in your mind is that during hydrogenation, I'm going to take both of the steps. First of all, I'm going to take about alkenes. Then I'm going to talk about alkynes. If I talk about alkenes, okay, I'm going to write over there. I'm going to write over here. Okay. If I talk about alkenes, this is my alkene. Here you can put hydrogen over here. The bonds that are left are basically the hydrogen bonds, right? Now, what you need to do is you need to do this reaction in the presence of what? In the presence of catalyst like nickel, platinum, palladium, right? And here you have to add hydrogen. That means you have to add H2 over here as the name suggests. And this will occur in the presence of nickel, palladium or platinum, any of these. Now these are what? These are the positive catalyst that basically increases the rate of reaction whenever they are used. Now students, when you'll be studying about surface chemistry, you'll get to know that there are positive as well as negative catalyst, one that increases the rate of reaction and the another one that decreases the rate of reaction. But here I am talking about what? Positive catalyst, which are going to increase the rate of reaction, right? Because they are going to provide the surface area for hydrogen to get adsorb. Now, what are these terms I am talking about? Adsorb, surface area. Don't worry, in the mechanism of hydrogenation, I am going to explain you in detail. First of all, learn to understand the basic general reaction over here. I have taken this alkene with me. This is what? This is alkene. Now here, As the name suggests, we are going to add hydrogen over here. So I'm adding hydrogen over here in the presence of this catalyst. Now what is going to happen? See, it is a very short kind of trick, you would say, or anything. You have to break this bond. You have to break this bond. Why you have to break this pi bond here? Because when you will break the pi bond, all the bonds will become what? Sigma bond, because there will be only single bond present between the carbon and carbon, and you want to obtain alkanes only. And alkanes are the one in which carbon and carbon contain single bond. So you know the product that you want to obtain are alkanes. But how to obtain it? I'm going to tell you. Here you have to break this pi bond and you have to add this H2. One hydrogen over here and another hydrogen over here. So what you are going to get over here? See, the carbon and carbon initially had one, the sigma bond that is represented as it is. And these two bonds are also represented as it is. Now, we have broken this pi bond, and one hydrogen is added to this carbon and another hydrogen is added to the another carbon. So what we are going to get? One hydrogen over here and another hydrogen over here, right? So kindly identify, is it an alkane molecule? Yes, ma'am, because we have seen that. I have already told you that kindly consider these as hydrogens. You can take for the case of another, instead of hydrogen, you can put any alkyl group also. It should be alkene molecule, that's it, right? But here I am taking a general case, so I am writing it like this. See, here carbon contains single bond. That means here we are obtaining what? Here we are obtaining alkane. Here we are obtaining alkene. Now, if I talk about alkyne molecule, this was alkenes, right? Now, let us take off what? Alkyne molecules over here. One second. Okay. Now, let us take one more case over here, that is alkynes. If I talk about alkynes refers to as triple bond between the carbon atoms. Here, let us take the simplest alkyne. This is alkyne. Now, here also we are going to add hydrogen in the presence of what? Nickel, platinum or palladium, any of these catalysts. Now, what is going to happen here? Kindly observe this very, very carefully. First of all, you are going to break number one, this pi bond, the very first bond, right? And these hydrogens are going to attack over here on both of these carbons. So what are you going to get? See, carbon contain first of all the single bond, then you have one more bond here. But the third bond is being broken over here, and two hydrogens are already present over here like this, and two have attacked over here like this, right? Now, here we are getting alkene molecule first. First we are getting what? We are getting an alkene molecule. Now students, now see here very carefully what we are going to do in another step. Here you need to remember, whenever you are preparing alkane from alkene, then you have to take 1 mole of H2. But whenever you are preparing alkane from alkyne molecule, you need to take 2 moles of H2. Now, if you take 2 moles of H2, it will again react with H2 in the presence of what? Nickel, palladium or platinum. Now, what you're going to get next time also, this bond is going to break, the pi bond, and these hydrogens are going to attack over both of these carbons, right? So what we are going to get over here, see, carbon and carbon initially contained single bond that was not broken, but the pi bond was broken, and hence hydrogens were attached over here. So what you are getting from this? You are getting an alkane molecule from this. You are getting what? You are getting an alkane molecule. So students, kindly observe that what is happening over here. If I talk about alkenes case, I am getting alkanes from alkenes by 1 mole of H2. But if I talk about alkyne case, then I'm first of all converting alkyne into alkene and then alkene into alkane, right? So this is the method of preparation from hydrogenation of unsaturated hydrocarbons. Now students, we need to understand the basic mechanism of this also, so that you don't get confused in your examination. This I have marked for you so that you don't get confused, right? Now let us move towards the mechanism of hydrogenation. We are going to do now the mechanism. If I talk about mechanism, students, see, first of all, we are going to take a nickel surface over here. What we are going to take? We are going to take this nickel surface. This is the nickel surface, or either take any of the catalyst surface. Okay, this is the surface. Now see students, what happens. First of all, we know that there is addition of hydrogen, right? So when there is addition of hydrogen over the surface, this is my H2. It will show interaction with the surface, right? So these are the bonds, that means they are showing interaction with the surface of the catalyst, right? Now students, what you need to observe over here, that we are basically taking an alkene case first. So we want that in the unsaturated hydrocarbon there should be hydrogenation. So what an alkene molecule will be doing, it will be approaching towards the hydrogen to make a bond with hydrogen, right? Now whenever this alkene is approaching towards hydrogen to make a bond, what is going to happen over here? Kindly see very carefully. Again, this is my surface, right? And over here, what I observe, that hydrogen and hydrogen bonds will break so that it can combine with carbon, because see, carbon has basically a valency of 4. Okay, so it will make only 4 bonds. To come and interact with it, it should break its one bond, otherwise it will be 5 valency for carbon. That is not possible. So what it is going to do is, first of all, this hydrogen is also going to break from here. It is also going to break from here. So what is going to happen? I am going to write this with the dotted, with the dash bond over here, that it is going to break, right? This bond is going to break. And now this carbon will be attacking over this hydrogen, and this will be reaching towards this hydrogen to show the interaction. Now what is going to happen? This is the carbon, right? Here we have 2 bonds over here like this. These 2 bonds I have shown. Here it had a single bond. Yes, it had a single bond. But now the pi bond is going to break in order to interact with hydrogen atom. In order to interact with hydrogen atom, the pi bond is going to break. So we are going to write it with, again, dash, right? Now what it is going to happen? The carbons are going to interact with the hydrogen. Hence there will be a bond formation between carbon and hydrogen. So all I would say, let us represent this also with the dotted ones. Now, first of all, let us write what is happening over here. Here, this bond is going to break. So this is bond breaking, that I'm going to write with BB. Here, this bond is going to form, this bond is going to form, and this bond is going to break. So this is what? This is bond formation. Clear, students? So now this state, whenever we are seeing that old bonds are breaking and new bonds are being formed, this state is basically known as transition state. Kindly understand, this state is called what? This is called transition state. Students, if you remember in the GOC portion, in the starting, I told you what are chemical reactions. We started from this topic and I told you chemical reactions are the one in which substrate is there, in which attacking reagent is there, and whenever they react with each other in the presence of some solvent, we obtain either transition state or we obtain either intermediates. Now, intermediates we have started in detail about carbocations, carboanions, carbon free radical, but what were transition state? During that, I told you old bonds are going to break and new bonds are going to form. So this is what transition state looks like. Here you can see the bond breakage is also occurring and bond formation is also occurring simultaneously, right? So this is transition state. Kindly keep in your mind. Here they can ask you in your MCQs that is there any carbocation being formed? No. Is there any carboanion being formed? No. Is there any carbon free radical being formed? No. There is a big no for the intermediates portion. There is no intermediate formation occurring. But if they ask you is there any transition state, so you will say yes, and it is going to be 4-membered, students. How come it is going to be 4-membered? Because see, 1 2 3, it is making a cycle, whenever there is a ring formation. So that what I'm going to tell you, there is a 4-membered ring being formed over here. Now what it is going to happen after this? Ma'am, we got to know that yes, bond breakage is occurring, bond formation is occurring, but does this whole structure is going to land over the surface of this catalyst? No. The catalyst here acts as a medium for the reaction to complete. That's it. It will get separate as it is without being consumed. It will get separate. It is just providing a medium for the reactant to be converted into product. That's it. So what we are getting, what we are observing over here, that catalyst is separated like this. Okay, and other than this, what we are getting over here, see this. Carbon contains single bond, yes. Here there are two bonds, other than this, yes. This bond is broken, so we are not going to show now. And these two bonds are being formed over here. So here, these bonds are being formed, and these are formed with which? Hydrogen atoms. Now, you can either take hydrogen over here, or you can either take any of the alkyl group. But what you are observing over here, that the carbon contains which bond? Single bond. And single bond is sigma bond, and sigma bond is what? Alkanes molecule. Alkane molecule over here. So what we are obtaining from here? We are obtaining alkane from here. So this was the basic mechanism that you need to keep in your mind about hydrogenation of unsaturated hydrocarbon, students. Now there are some of the important points that you need to keep in your mind. Right, important key points. Transition state is formed, first of all. Other than this, students, no intermediates are formed. No intermediates are formed. Now, intermediates are basically here carbocations, carboanions, carbon-free radical. Okay, all of these are not formed over here, right? Other than this, students, four-membered transition state is obtained. Okay, now one different point that you need to keep in your mind, the rate of reaction. If I talk about rate of reaction in the case of alkenes and alkynes, which will have more rate of reaction? Kindly consider this question very seriously. Which will have more rate of reaction? I'm talking about alkenes and alkynes. If I'm going to take a reactant as my alkene alkyne, I obtain that alkynes are the basically ones which have more rate of reaction. Why? Because it has a linear structure. When it has a linear structure, it will interact with the surface of nickel or platinum or palladium very easily. But alkenes, due to its structure, will not interact so much as compared to alkynes, right? So if I talk about the rate of reaction in alkenes and alkynes, alkynes basically have more rate of reaction as compared to alkenes. Other than this, if I talk about rate of reaction, that rate of reaction is inversely proportional to steric hindrance. Now, what do you mean by steric hindrance over here? Steric hindrance basically refers to as the bulky group. What are you talking about this, ma'am? Kindly explain in detail. If I talk in detail, I would say, let us take one example of alkenes over here. Okay, for example, you have the simplest alkene molecule first of all here. Then you are going to get one second. Basically here Me refers to as methyl group, that is CH3 group. You have these four structures. If I'm going to name this is your A, it is going to be your B, this is C, while this is D. Now I'm asking you, what is the order of rate of reaction in A, B, C, D? What you're going to say is that, ma'am, bulky groups are the one See, hydrogen is not a bulky group, but if I say I'll replace one hydrogen with one methyl group, it is a bulky group. This is a bulky group over here. If I talk in this case, these two are the bulky groups that are present over here. And if I see this case, there are basically 4 bulky groups that are present over here. Now, what do bulky groups do? Bulky groups are basically what they are going to do. They are going to repel these of these structures, right? So whenever there are more bulky groups, either you see directly there are 4 bulky groups over here, there are 2 over here, there is 1 over here. So more the bulky groups, more is the steric hindrance, and more is the steric hindrance, the rate of reaction decreases. So I would say that A will have rate of reaction more than B, than C, and at the last D. So D has the least, rate of reaction. Why D has the least rate of reaction, students? Because D has more bulky groups in it, right? So this was all about hydrogenation of unsaturated hydrocarbon, students. Now comes the next method of preparation, that is basically from alkyl halides. If I talk about from alkyl halides, number first that comes in our mind is direct combination. If I talk about, first of all, what are alkyl halides? So alkyl halides are basically RX, where R is the alkyl group and X is the halide one, halogen one, fluorine, chlorine, bromine, iodine. But in this case, what you are going to observe, first of all, let us take one case, one example of the alkyl halide. The simplest one, that is methyl chloride, CH3Cl. Okay, this is your alkyl halide. Now what you need to do is you need to react this in the presence of Zn and H positive. You need to react this in the presence of zinc and H positive, that is acid. You need to react it. What you're going to obtain over here is that one of the hydrogen is going to react with CH3 and one hydrogen is going to react with Cl. This bond will break from this. This RX bond is going to break. So when it is going to break, one hydrogen is going to attach with these sides and we are going to get CH3H plus HCl. See, this bond is going to break, the RX bond is going to break, and both of them are going to get one hydrogen over here. So this is direct combination which occurs in the presence of Zn and H positive. Okay, now let us take one more case over here. CH3, CH2Cl. So here also H2 is going to react, one hydrogen is coming here and one hydrogen is coming over here. So what we are going to get? CH3, CH3 plus HCl, right, students? Now, one basic thing that you need to keep in your mind, what are you obtaining from here? You are obtaining an alkane molecule from here. This alkane molecule is what? It is methane. While if I talk about this alkane molecule, it is what? It is ethane. This is ethane, this is methane, right, students? So in this way, you can clearly do these kinds of questions very easily. Now, if I talk in alkyl halides only, there is one exception. There is one exception. If I talk about the exception, that is alkyl fluorides. For the case of alkyl fluorides, direct combination won't occur. Why it won't occur? Because, students, alkyl fluorides are highly polar in nature. Why alkyl fluorides are highly polar? Because, alkyl fluorides, that means RF. Here we know that this R group contains basically the carbon, right? And fluorine is the most electronegative atom. It is the most electronegative atom, due to which there is highly polar bond between these, due to which it is strong in nature, and hence to break this bond, because we are breaking this bond, no, so to break this bond more amount of energy is required. That's why there is no direct combination that occurs for the case of alkyl fluoride, but it will occur for the case of alkyl chloride, bromide and iodide. Clear, students? So this was from the direct combination method. Now comes the most important topic, that is going to be the Woods reaction. It also lies in the category of alkyl halides, but students, it is the most important you need to keep in your mind about Woods reaction. What is Woods reaction? If I talk about Woods reaction, so Wood reactions basically occur in the presence of sodium and dry ether. What is happening over here? See, for example, I take again methyl chloride. I am reacting this with sodium and I am taking 2 moles of this, right? So here I am writing this CH3Cl twice and it occurs in the presence of dry ether, and sodium also you have to take twice, right? So what is happening over here, kindly listen very carefully. See, this 2Na are going to combine with the 2Cl which are present in both of these molecules, right? So first of all we are going to get 2NaCl. Other than this, what we are going to get, see, when 2NaCl are combined, 2NaCl are separated, what is left over here? One is CH3 and one is CH3. So they both will combine and will form what? It will form an ethane. These CH3 will combine and will form ethane, right? So what is the basic thing that we observe over here? That the reactant which we are using contains a single carbon, but the product that we are obtaining contains twice the number of carbons as that of reactant. So here we have taken 1 carbon. Yes, we have taken 2 moles, but we have taken 1 carbon. But here if I talk about the structure, we are getting 2 carbons. So whenever you are using Wood's reaction, you will see very different cases. In one of the cases you are going to get the double of it. In some of the cases you are not going to get the double of it. There are many cases. I'm going to tell you one by one. Let us take one more case like this only. First of all, let us take this general reactions. CH3 CH2Cl plus 2Na. Now take this twice, directly you can write this. What you're going to get, 2 NAs are going to combine with 2 Cl. So yes, 2 NaCl is going to come out. Other than this, what is left? We are left with 2 CH3 CH2. Now what is going to happen? CH3 CH2 CH2 CH3. Now what do you observe over here? 2 carbons were taken, but we are getting how many carbons? 4 carbons. We are getting butane from here. Now students, if I ask you, kindly prepare propane from this reactant only. How will you obtain propane from this reaction? So there are basically different cases, as I already told you. The very first case is the simple case that we have already seen, right? Now comes the next case, students, that we need to know over here. Okay, this was the very simplest case that we have seen over here. Now, if I talk about the next case, students, we can see that there is a mechanism that we need to understand first of all. The mechanism is free radical mechanism. And if I talk about free radical mechanism, it will help us to know that which of the following product is being obtained over here. So, first of all, write mechanism here. Okay. If I talk about mechanism, it is free radical mechanism. It is what? It is a free radical mechanism. Now what is happening over here, students? First of all, the sodium, it splits into Na positive and an electron. This is going to happen. Then what happens? We know that we are taking alkyl halide. For example, we took methyl chloride over here. So what is going to be happen over here? That these contain 2 electrons. 1 electron this will take, another it will take. So what we are going to get? We are going to get 1 R radical and 1 X radical. Now this X radical, students, combines with electron and forms X negative. Okay, and this X negative further reacts with this Na positive to form NaX, like we form NaCl. Similarly, this is the basic thing that we need to keep in our mind. Now, what is left over here? This electron is being consumed. This X radical is combining with electron. This X negative is joining with Na positive. The one thing that is not being used over here is this R radical. Now, what we are going to observe from this, that R radical, now what happens? This R radical either combines with itself and form RR bond. Okay, now this is basically what? This is the combination. This is the combination reaction. This is what? This is combination. Let us take one example to understand combination in detail. If I talk about combination, I am taking here CH3 CH2. If I took CH3 CH2X, then CH3 CH2 radical will be obtained. So I am directly writing it. Now, both of the times these radical will form a bond and will form CH3 CH2 CH2 CH3, which we have already seen butane is formed. But now comes the next case, which is disproportionation. Now in the case of disproportionation, what happens, students? You will write these as same but in a different way. How come? See, CH3 CH2 radical plus. Kindly open one hydrogen from this CH3 and write this as HCH2 CH2 radical. Now what will happen over here? Kindly see what will happen. This bond will break and this one electron will react with this one electron of CH2, and this one electron will react with this CH2 radical, right? One electron. So what we are going to see? We are going to see this bond is going to break from here and we are going to get CH3 CH3 plus. Now see, this hydrogen is reacting with this forming CH3 CH3, but this here one radical radical is making one bond, hence here CH2 double bond CH2 is obtained. That means an alkene can also be prepared from the Woods reaction. See, we have seen in the case of Woods reaction, we can obtain alkanes also, double the alkanes, that is butane. We can obtain alkenes also in the case of disproportionation. Now for different alkyl halides, which one is going to be valid? If I talk about primary and secondary alkyl halides, for 1 degree alkyl halide and 2 degree alkyl halide, you know, this is valid, this one, combination one. If I talk about disproportionation one, 3 degree alkyl halide is valid. See, all of these can make both of these structures, like these can also make this, these can also make this, but most favorable are these one. The most favorable for 1 degree alkyl halide and 2 degree alkyl halide is the combination one, and most favorable for our disproportionation for 3 degree alkyl halide is disproportionation. Now students, comes the next topic, basically that is the types of Woods reaction. Okay. If I talk about the types of Wood reaction, basically there are intramolecular and intermolecular. Now, first of all, I am talking about intermolecular. In intermolecular, we have already seen the case, so I am directly writing the case for you. That is simple. If I take R radical plus R radical, it will form RR bond. It is the basic that we have already seen. But now, what I do, if I take another case, if I am taking two alkyl halides, for example, R1X plus R2X, and I am taking again 2Na. What I am getting from here? I am going to obtain 2NaX from here. And I know that these two are going to combine like we did in the previous structure. R and R is going to combine. So here R1, R2 can combine. Moreover, R1 can combine with itself also. R1 can combine with itself also, forming R1, R1 bond, and R2 can combine with itself also, forming R2, R2 bond. So here in this, what do we obtain? We can see that basically 3 more structures are made with NX. Clear? So this was our first kind of reaction, that is intermolecular. Now comes the next one, in which we are going to see 2 cases. One is 1,2 dihalide, another one is 1,3 dihalide. Now if I take the next case, okay, if I take the next case, that is 1,2 dihalide. Now for the case of 1,2 dihalide, what happens? What is 1,2 dihalide? For example, this is the carbons. These are the halogen that are attached over first and second carbon, right? So this is 1,2 dihalide. Now, for example, this is first carbon, this is second. So these are 1,2 dihalide. Di refers to 2, halide refers to halogen groups. Now for this case, students, what is going to happen? We are going to observe that this bond is going to break. This one electron it is going to take with itself. This is going to take electron with itself. This is going to take electron with itself. This is going to take electron with itself. What we are observing over here, that here students, these 1 electrons are going to make a bond in between these and making a double bond over here like this. These 1 combine. This also contain 1 radical. This also contain 1 radical. They both will combine with each other. Now what happens if I take 1,3 radical? 1,3 not 1,3 radical, 1,3 dihalide. For the case of 1,3 dihalide, for example, now on the first carbon and on the third carbon, we are going to see the halogen groups like this. Right? Now what it is going to happen in the same way, this 1 electron is moving here, this 1 electron is moving here, this 1 electron is moving here, this 1 electron is moving here. So what we are observing here, there is a C radical over here, then CH2, then C radical. Now this one C radical will combine with this C radical, forming what? Forming a ring like structure like this. Carbon, 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 forming hydrogen, Hydrogen, hydrogen. You can either make this, in another way, but you will form a ring-like structure over here. You can see that these two will combine, and the first carbon is when it is attached with the last carbon, it makes a ring-like structure, students, right? So these are the types of wood reaction. Now, students, we will proceed towards our next kind of reaction. So students, now comes our next topic, that is decarboxylation. If I talk about decarboxylation, first of all, we are taking here carboxylic acid, that is CH3COOH. Now, if we are going to name this CH3COOH, what it is name? It is ethanoic acid. Why? Because here carboxylic group, that is COH, is also included in the naming of parent chain, right? So during the naming, this is included. This is the first carbon, this is the second carbon, hence two carbon atoms. So the word root is eth. There are single bond between the carbon atoms, so ane will come. And we know that it is carboxylic acid, so the suffix that we are going to use over here is oic acid. And ethane ends with E and oic acid starts with O, hence E will not come. Ethanoic acid will come, right? So here as a reactant we are taking ethanoic acid. Now it is going to react with NaOH. It is going to react with NaOH, students. Now what is going to happen over here? Water is going to come out from this. How come water is going to come out? See, one from this hydrogen, and if you see here, if you see over here, this OH group and this H is going to come out. That is H2O will come out. What you are going to obtain over here is CH3 C double bond O ONA. Now students, this is very important for you to understand. This is sodium ethonate. It is known as sodium ethonate. Okay, what we have done is we have taken ethanoic acid, reacted with NaOH, water is being taken out, and we obtain CH3COOONA. Where students, you know that it further reacts with soda lime, that is CaO plus NaOH. It further reacts with soda lime, CaO plus NaOH, students. Now, when it reacts with soda lime, students, we get here methane. What is the product obtained here is methane, that is CH4. Okay, other than this, students, we obtain Na2CO3 here. Na2CO3 here. Right? So what happens over here? You can directly see what we have done. We have taken ethanoic acid, reacted with NaOH, water being removed. We obtained sodium ethonate, which further reacted with soda lime, which is CaO, calcium oxide plus NaOH, and gave us the product methane. Right? Plus we obtained Na2CO3 from this side. So this was all about decarboxylation, students. Now comes our next reaction, that is coal-based electrolysis. What do you mean by coal-based electrolysis? Here we are going to take salt of carboxylic acid. What we are going to take? Salt of carboxylic acid. Okay, we are going to take the salt of carboxylic acid in the presence of electrolysis. Now, what do you mean by electrolysis? In the chapter, if you will see in your 12th class, when you are going to study electrochemistry, you will observe that basically electrolysis is the conversion of electrical energy into chemical to perform the chemical reactions, right? So what we are going to see over here is that when we take salt of carboxylic acid and electrolysis is done, we obtain CO2 and here the byproduct. Now, if I take the carboxylic acid as CH3COOH, this is going to be my reactant, students. I am going to take 2 moles of this. Okay. Now, when it is going to react, it is going to react with water. Okay. It is going to react with water and electrolysis occurs over here. And we obtain CO2. Okay. We obtain CO2 from this side and we obtain CH3, that means ethane. Here ethane is produced. Students. So this is basically the coal-based electrolysis process. Other than this, we can also take, instead of water, we can take NaOH. And when we take NaOH, like decarboxylation, the reaction occurs. When we take CH3COH and react it with NaOH, what do we obtain? We obtain that water is being removed from this side. We obtain sodium ethonate, that is CH3, C double bond O, ONA, like we did in the decarboxylation process. Now the next step is similar to this. What we are going to see? We are going to see that two water molecules are taken out, and hence we obtain NaOH plus CO2, students, and the main product, that is ethane, which is being obtained here. Okay, so these are the two reactions that you need to keep in your mind while doing coal-based electrolysis, students. Hopefully it is clear to you. Both of these reactions, it is quite simple. I'm going to repeat it again for you. In the very first reaction, we took water and electrolysis happened and we obtained ethane molecule plus CO2. In the next reaction, we took NaOH and the reaction occurred and we got sodium ethonate just like the previous case, and we obtained NaOH plus CO2 plus ethane, right? Other than this, students, what we need to keep in our mind, we need to keep in our mind its mechanism. What is the mechanism for this? If I talk about mechanism, students, first of all, see, in some of the cases, what you're going to see, in some of the cases, you are going to get RCOOK. There may be some of the cases, in that also you need to first make just like structure, just like ethonate. You're going to, free radical mechanism, and you will separate R radical from that, and that R radical is going to combine and form the product. For example, if I talk about this case also here, what do we see here? When I'm going to explain you the mechanism, see here, CO2 will separate out, and this CH3 will, combine with its own radical CH3 and will form ethane. So in the when you are going to study the mechanism, you are going to get the reaction in depth. So in the previous cases, I told you about general cases first, then I told you about mechanism. So this was the way of doing a reaction. Now in this case also I've given you general, but these general might be sound confusing for you, but don't worry. When you will get to know the mechanism, it will be very easy for you to understand. For mechanism, here we obtain that there are two cases. One is anode one, another is cathode one. So sorry, if I see here CH3COOONA, we have this with us, right? Sodium ethonate. Now here oxygen has negative while sodium has a positive sign on it. What happens over here? This sodium gets separated. When it gets separated, it becomes Na positive. And what do we obtain over here? We obtain CH3 C double bond O negative. And yes, Na positive is separated from this side. Now students, what happens? As you know, this is an anion. So anion will move towards the anode because it is electrolysis. So here anode and cathode both will be considered. Now if I talk about anode, at anode, as I told you, which will go? Anion will go, because from A anode, A anion. You can study in this way. Now this, if you'll take, this is what? This is your anion molecule. Now what happens over here? Kindly take out 2 electrons from here. If you'll take out 2 electrons from here, I have taken 2 moles of this, right? What do you observe here? There is a bond breakage here. This bond will break over here. Now this, electron will move here, and we have taken 2 moles. Why 2 moles? Because CH3 radical will combine with CH3 radical, right? And this will be separated out. Here, this will be separated out. Now for the next case, what you are going to do? What you are going to observe over here? You are going to observe over here that this bond is separated and this bond is separated, right? Now next, students, what? Next you are going to get CH3 single bond CH3. Hence it is clear to you. So this was what? At anode we obtained ethane, as well as CO2 is being produced. Here CO2 is being produced, as well as what? Ethane is being produced. How ethane? This CH3 radical is obtained, and this CH3 will combine with CH3 forming ethane molecule. Now this was at anode. Now what will occur at cathode? The question arises, what will occur at cathode? At anode, kindly remember, you have taken the anion, it will going to react. At cathode, you had water with you. Okay, so what will happen? The 2 water molecules that you took will lose electrons and split into H positive and OH negative. right? This thing you clearly know. But here, students, this is the basic reaction that we know. But I am telling you, it will lose 2 electrons, leaving. When it will lose 2 electrons, we will get over here 2H radicals and OH negative. Okay, when you are taking out 2 electrons from here, you are getting 2H radical. I can write in the radical form. Why I have written the radical form? For you to understand it very carefully. Now this H radical, you can directly also write it as like this. H radical combines with H radical, forming H2. Either you can directly write it as like this, or you can write it as in the form of radical. Now the next terms come that 2OH negative will combine with 2Na positive, forming 2NaOH. Now, if I talk about the important points in this reaction, what you have seen, kindly see here. You have seen at anode, we obtain ethane and CO2. That means at anode, we are obtaining what? Alkane and CO2. So the most important point is alkane and CO2 are obtained at anode, while NaOH is obtained at NaOH also H2 is obtained at cathode. These were the 2 points that you need to keep in your mind while doing this reaction. Other than this, students, here what you observe that you can never obtain methane. You can never obtain. Why? See here. See here, why you can never obtain methane? Because at least here if you have one CH3, CH3 will combine with CH3 forming a 2 carbon compound. That means you can never form methane. You will always form the simplest alkane that can be formed here is ethane, not methane. So methane can never be formed. Methane can never be formed. Ethane is the simplest alkane obtained. Ethane will be your simplest alkane that can be obtained, right, students? Now you need to keep in your mind at anode oxidation occurs while at cathode reduction occurs. Now this was all about coal-based electrolysis, students. Now we are going to see our next reaction. So students, now comes our next reaction, next method of preparation, that is going to be Franklin reaction. In Franklin reaction, we are going to take 2 alkyl halides and we are going to react it with Zn. See, I have written this opposite, it is the same thing. Now what happens over here, this combines, that means ZnX2 is liberated over here, and the other product that we get over here is the bond between R and R. Right? So it is also a method of preparation for alkanes. Now let us see one of the cases for it to understand more clearly. If I take CH3, CH2Cl reacted with CH3, CH2Cl and with Zn. So if I ask you what is the product, first of all you will rearrange them. You will write CH3, CH2Cl plus Zn plus Cl, CH2, CH3. We will see that here Zn Cl2 will be liberated out. Zn Cl2 will be liberated out, leaving CH3, CH2, CH2 also as a product. See, now this CH3, CH2 will combine with this CH2, CH3 forming CH3, CH2, CH2, CH3, which is an alkane. So this is also our method of preparation. Now students, comes our next method of preparation, that is Corey-House synthesis. If I talk about Corey-House synthesis, here also we are going to take alkyl halide. In 3 steps it is going to occur, that is Li, then the next step is CuCl, the next step is Rx. If I see over here what is going to happen in a direct method, whenever you are going to get in the question paper, you are not going to do it with the mechanism step. You are going to do it directly. So what you need to keep in your mind is that just connect both of these. If it is R dash, then it will be R dash. If it is same RR, then it is connected. How come? See, R radical will combine with R radical forming R bond R, that is alkane. It is a direct method. No need to see what is the byproducts obtained. We just want to obtain alkane. That's it, right? Just combine both of these. If they're different, then also combine both of these. There is no worry. Now comes the mechanism portion, students. If I talk about mechanism, first of all, this Rx will react with Li forming RLi. This is the very first step. Now comes the second step, that is with the CuCl forming Gilman's reagent, students, which is R2CuCl. Li. Because here is Li, here is Cu. It will form R2CuLi, which is Gilman's reagent, which on further reaction, students, with Rx is going to form two kinds of product. One is ionic, another one is covalent. Ionic one is going to be RLi. That means here R is negative, Li is positive, plus RCu. This is our covalent, while this is the ionic product that is being obtained. Clear? Now in the very next step, what is going to happen, students? This R will combine with this R directly, or you can see here. Kindly forget this, students. What you're going to observe over here is that you are going to see that here X negative was liberated. First of all, see this. X negative was liberated. That X negative will combine with this, or I would say it will combine with this, leaving LIX. Or either you can say here we have taken Rx, it will combine with this. It is the same thing. We took here alkyl halide, again we took here alkyl halide. So this alkyl halide, this halogen will react with the positive portion, and this R will be reacting with this, because here, see what happens. This is bond is broken, this bond is broken, right? So here this R is going to combine with this R, forming RR bond. Other than this, what is left over here? This covalent bond, RCu. So these are the products that are obtained over here. That is LIX, RR, and the another one is RCu. Now students, here the attack of this one, carbonion. The attack of this carbonion, this step is basically the rate determining step that you need to keep in your mind. And this is basically useful for preparing unsymmetrical alkanes. Clear? Now students, how for unsymmetrical alkanes? Because here R dash can be different and here R can be different. So you can obtain for unsymmetrical also. Now students, this is what? This was our methods of preparation of alkanes, which we have covered. Now I am going to move forward towards what? Towards physical properties and chemical properties. Once I want you all to revise it, because these are the reactions that you can't forget. Okay, now see, these were all about alkanes. That was the general thing. Here what you need to keep in your mind, I'm just putting a star mark over here on all those topics that are important. Why I'm revising it? Because first of all we will cover alkanes, then alkenes, then alkenes, and then alkynes. So what we are going to observe, first we will do method of preparation, physical property, chemical property. So I don't want in one shot video lecture for you to get mixed up. That's why I'm revising it. See, fastly we are going to do is, this is the molecular formula that we need to remember. Other than this, they are known as paraffins, right? Because the ability for the bond formation, they have the little ability for the bond formation. Little, para refers to little, affinity refers to the tendency to make the bonds. Other than this, the structure, right? Here carbon is sp3 hybridized and it is tetrahedral, while they are inert at the room temperature and the normal conditions. This was about alkanes. Moving to the methods of preparation, from where the important segment starts. Here you need to keep in your mind, whenever you are doing hydrogenation, my dear students, you have to break the pi bonds and you have to add the hydrogen. For the alkenes, only you require one H2 molecule. It will occur in the presence of what? Nickel, palladium and platinum. Clear? And for the alkynes case, first it will convert into alkenes and then into alkanes portion. Clear? It will also occur in the presence of what? Nickel, platinum and palladium. Now its mechanism portion. I have told you for the mechanism portion you require a catalyst, and this is a surface phenomena. Adsorption is occurring over here. Don't get confused between absorption and adsorption. Adsorption refers to the surface phenomena, the interaction with the surface molecules, while absorption refers to the interaction with the bulk one. Here the interaction of H2 molecule with the catalyst is occurring on the surface only, right? So do not forget this point also. Here adsorption is occurring. What happens over here? Their bond is being broken between hydrogen, and the carbon is going to attack here. So here bond breakage and bond formation occurs, which is known as transition state. And at last we are obtaining what? Alkanes. Clear? Okay. Now comes the important key points. Transition state is formed. No intermediates are formed. These two are very, very important. Other than this, rate of reaction of alkynes is more than alkenes. Why? Because alkynes are linear in shape. Now you can revise with me. Good. Okay. Here rate of reaction is inversely proportional to what? Steric hindrance. Clear? This was the question which I have already told you. Okay. Other than this, we have the method of preparation for the alkyl halide. Now for the alkyl halide, this is the general case and I know you people can do this very easily. So I won't mark this as most important because it is not most important. It is okay. This topic is very easy because here one hydrogen is going to attack on the alkyl group and another on the halide group, right? So we are going to obtain the products. Now comes the Woods reaction, the most important one. We have already given the star marks over here, so I would give another here. I would give this. No, I would give a flag over here. Yes, because it is important. Woods reaction is important. In Woods reaction, do remember you have to take dry ether. Right? Now students, here you are taking 2 moles. 2 moles of the reactant plus 2 moles of Ni. So that 2 NaCl can be obtained and this CH3 will combine forming ethane. If we take here 2 Cl will combine with 2 Na forming NaCl and we will be left with CH3CH2. They both will combine with each other leading to the formation of alkane, that is the butane. Now here one more question arised. Why do we obtain a product that contains twice the number of carbons? Can we obtain another one also? Yes. So there is one more example for you, this one. If I talk about the combination reaction, it is quite simple, which we have seen, and it occurs for the primary alkyl halide and secondary halide. But if I talk about disproportionation one, here what happens? Here alkene is formed. This is very important. Here alkene is formed in this case. Clear? Okay. Now coming to the types of Wood reaction, this is also important, where you are taking different kinds of alkyl halides. For example, here R1X is taken, here R2X is taken. So different alkyl halides are taken. So first case is they both will combine with each other. Second, it will combine with itself. It will combine with itself. So here 3 products are obtained rather other than NX, right? Now students, come 1,2-dihalide and 1,3-dihalide. In 1,2-dihalide you obtain alkene and in 1,3 you obtain cycloalkane, right? Okay, now comes decarboxylation. For decarboxylation, it is quite easy for you to understand that you have to do in the presence of NaOH. Water will be liberated. When water will be liberated, sodium ethonate will be formed, and with the help of soda lime, the product that is obtained is methane and Na2CO3. Okay. Now, students, this is quite important. Coal-based electrolysis, it is quite important. Here what happens here is we are going to obtain this anion. Now what happens? Here 2 electrons are liberated, this bond is broken up, and here this CH3 will combine with CH3 forming a ethane molecule and CO2 is liberated. What we need to keep in our mind, at anode alkanes are produced and CO2 are produced, while at cathode H2 and NaOH is produced. Other than this, you have to just observe the mechanism for anode and cathode sake, right? Okay, students. Now seeing the Frank-Land reduction, it is also easy. I won't mark it as an important because it is quite easy. Whenever you are going to see in the reaction, you just have to take Z and Cl2 out, Z and X2 out. That's it. And the rest over is combined with each other. So it is quite easy. Okay, now comes the Core-House synthesis. For Core-House synthesis, I would say there is a 3-step reaction that we have already seen. The best trick to remember is kindly attach both of these, because in examination there is no need for you to do the mechanism work, right? So students, this was all about our methods of preparation. Now we will move forward towards the physical properties of alkanes. So students, now looking towards the physical properties, the very first physical property, if I talk about alkanes, is that alkanes basically are non-polar in nature. They have very less polarity. So the very first physical property is that alkanes are non-polar in nature. In bracket, you can also write very, very less polarity. Why is it so, students? Because carbon and hydrogen, they almost have same electronegativity. That's why. If I talk about this case, right? Ethane. Or any case you can take of any alkanes. I am saying that the carbon and hydrogen, the bond that they make, both of them have almost same electronegativity. So there is no electronegativity difference. See, whenever we see the electronegativity difference, there arises poles. That means polarity difference arises. But if there is no electronegativity difference, then it is referred to as non-polar. So hence it is non-polar in nature, students. Next is that we are going to see the nature. For example, if I am saying at room temperature, carbon first to carbon fourth are gas at room temperature. Then carbon fifth to carbon 17th are liquid at room temperature. You should remember this, that carbon number first. I am talking about alkanes from carbon 1 to carbon fourth. Okay. Sorry. Okay. Carbon 1 to carbon 4. That means from methane to butane. All of these are what? All of these are gas at room temperature. And if I talk about carbon 5 to carbon 17, students, they are liquid at room temperature. These are their physical states if we talk about. And from, carbon 18, they are waxy solid like structure. Like, for example, Vaseline, they are waxy solid like structure. So I would say from carbon 18 to onwards, they are waxy solid. Again at room temperature. So the very first property was quite easy. The second one also was quite easy. Now, if I talk about being non-polar in nature, in which of the following they will be soluble or insoluble? If they are non-polar in nature, then they are easily soluble in non-polar solvents. Okay. So the third point is, due to their non-polar nature, they are easily soluble in non-polar solvents. Non-polar solvents. Clear, students? Now, students, moving on to the next property, that is the boiling point. If I talk about boiling point, boiling point is directly proportional to the molecular mass. It is directly proportional to the molecular mass, students. As well as if I talk about boiling point, it is inversely proportional to branching also. So whenever you observe branching, their boiling point comes out to be low. Clear? Now, if I talk about melting point case, if I talk about melting point case, then melting point is also directly proportional to molecular mass. Hence, if number of carbon increases, the the melting point also increases with it, students. But alkanes with even number of carbon atoms have more melting point. Okay, do remember that. But alkanes with even number of carbon have more melting point. More melting point. So these are the points that you need to remember during the physical properties of alkanes. I would repeat it, and the important one are these ones. These both. Why? Because the question arises in your examination regarding the branching portion. Okay. So you should remember, where there is branching, there is less boiling point. Okay. Do remember that. And for the melting point also, Do remember it is directly proportional to the number of carbons, that means molecular mass, as well as the even number of carbons will have more melting point. Clear, students? Now we will see the chemical properties of alkanes. So students, looking forward towards the chemical properties. Chemical properties of alkanes. Now, it is also an important topic, students. This is also an important topic. Okay. Now, if I talk about chemical properties, the very first chemical property that I'm going to tell you is a substitution reaction. If I talk in chemical properties, number first is substitution reaction. Now, what do you mean by substitution reaction? See, we have already covered this in the GOC section at the very end when I told you about the types of reaction. Basically, substitution reactions are those reactions in which one of the reactant is being substituted by another group. You know, it takes place of another group. That means it's to substitute, to take place of another. That is substitution reaction. So alkanes basically is either replaced by halogen, nitro or sulfonic group. Okay. So you need to remember alkane is replaced by either halogen, nitro group or sulfo group. Okay, so whenever it is replaced by halogen, it is known as halogenation. Do remember? Now here, one thing more. Here alkane hydrogen will come because see here, if I talk about CH4. Now, how to substitute? From CH4, one hydrogen is being substituted by another group. You know, from here I can also write it as CH3H. So there will be removal of this hydrogen and something will come in place of it. So alkanes hydrogen is replaced by either halogen, nitro group or sulfur group. Kindly correct it. Okay. Now when it is replaced by halogens are your what? Fluorine, chlorine, bromine, iodine, by them. Okay. When they are replaced by halogens, it is called as halogenation. It is known as halogenation, students. And when I talk about nitration, HNO3 is used. And when I talk about sulfonation, H2SO4 is used. Okay, now one by one we are going to see. So the very first that we need to understand is halogenation. The very first we will understand is halogenation. Now you have got that hydrogen will be substituted by halogen, that is halogenation. That is quite easy for you to understand. Students, other than this, it always occurs in the presence of sunlight or at higher temperature. Do remember that? Always occurs in the presence of sunlight and at higher temperatures or high temperature. Clear? Now students, in halogenation we see various cases like bromination, iodination, chlorination. We see a lot of cases. So if I talk about the order of reactivity, the 3-degree alkanes order will be more than the 2-degree and then the 1-degree. Kindly remember this in your mind. Keep this in your mind. Now I'm going to do chlorination process. In the chlorination process, let us take one example. If I take one example, that is of CH4 and it is reacted with Cl2, right? Halogenation means the addition of halogen and the replacement of hydrogen. So from CH4, one hydrogen will be replaced by and will be substituted by what? By halogen. By which halogen? Chlorine. So what we are getting over here, we will get CH3Cl plus here we will get what? HCl. Right? See here, this hydrogen that is being removed from CH4 is now attached with this Cl. Now one Cl is left, that will be reacting with the CH3, right? Now it occurs in the presence of sunlight. It occurs in the presence of sunlight. Now in the next step, now see, when we are taking excess of chlorine, then it keeps on reacting again and again. Now here CH3Cl is produced. It will again react with Cl2 in the presence of sunlight, leading to the formation of CH2Cl2. Again, one hydrogen will be removed and one Cl will substitute and it takes its place. So here HCl will be taken out. Now in the very next step, CH2Cl2 will react with Cl2, leading to the formation of CHCl3 plus HCl. This CHCl3 is known as chloroform. Clear? Now this CHCl3, students, will react with Cl2, leading to the formation of CCl4. CCl4. Clear? So basically this is the chlorination process. Here we have taken Cl2 in excess, students, right? Now students, I2 reacts slowly. This is chlorination. If I talk about iodination, iodination reacts slowly, therefore it must be used with the reagent known as HiO3, right? So during halogenation this occurs. So this was about chlorination. If I talk about iodination, you shall write it. Because in the case of iodination, we are using HiO3 for this reaction to take place. Do remember this. Iodination will not occur if it is done just like chlorination, because it is a slow process. So we use a reagent HiO3, and if I show you the reaction, it is going to be CH4 plus I2. Basically what happens over here, when CH4 plus I2 is done, it is done in the presence of 772 kelvins. Sorry, 773 kelvins, my dear students. And here what do we observe? According to chlorination process, one hydrogen was taken out and iodine would come here. So here CH3I would be formed plus HI, but yes, it doesn't occur. Why? Because it is a reversible process. When CH3I and HI are produced, it will revert back to the reactants. So we are using HiO3 so that reversible reaction doesn't take place. So HiO3 is used so to stop this reversible process. Right? Now, how does it react? HiO3, students, will react with this HI now. HiO3 will react with HI. When this will react with HI, it will lead to the formation of iodine, students. Iodine will be formed plus water will be liberated out. So hence now it is not a reversible reaction. The reaction stops here. So basically iodination is not possible because it is a reversible reaction. To make it possible, we require HiO3. But when we make HiO3, the product formed is not an alkane molecule. It is I2. It is not an alkane molecule. I2 is formed. Now comes, students, about nitration. As we have seen in halogenation, halogen was substituted at the place of hydrogen and it took its place, right? Now in the case of nitration, we are going to use HNO3. Now what happens over here? We are going to take our alkane molecule. We are going to react with it, HNO3. Here there is a coordinate bond between nitrogen and oxygen. Now what happens over here, students? Kindly see this very carefully. See, here a bond breakage occurred. This bond is broken up. So here we get OH radical. Similarly, here the bond breakage occur, we get H radical. Now OH radical and H radical combines to form what? Water. And what is left over here is R radical and this one. So what we get over here is RNO2. What we are getting over here is RNO2 is obtained. So this is very simple process for nitrogen. It is just like that. Okay. Now in the examination only R group will be changed, like CH3, C2H, CH3, CH2. Okay, so you just have to do the direct reaction. That's it. Okay, kindly take the water out and rest combine both of them. Now comes the next case similar to this is sulfonation, students. Now, if I talk about sulfonation only, here also we are going to take our alkane molecule, students. As I told you, we are going to take H2SO4 right now. Okay, so here, okay, students, so here H2SO4, so H2SO4, right? This occurs. Now, again, similar to nitrogen, here also bond cleavage will occur. And so, this bond will be broken. R radical, H radical. Now, what happens over here? H radical will combine with whom? OH radical, right? So, here this bond cleavage occurs. What we are getting over here is water, because OH radical plus H radical forms water. Now this R radical is going to combine with this sulfur, forming R S double bond O double bond O OH. Clear, students? This is RSO3H. This is the process for sulfonation. This is the easiest step I would say for nitration and sulfonation, right, students? Now comes, students, the next chemical property, that is combustion. That is combustion. If I talk about combustion, what do you refer to as combustion? When there is a reaction in the presence of oxygen, that is referred to as combustion. So here, see, CH4 plus O2 gives CO2 plus water. So during combustion, we obtain CO2 plus water. It occurs in the presence of oxygen. Do write this. Occurs in presence of oxygen, that is O2. Now this was the reaction for the methane case. You can kindly balance it out accordingly, and here heat is also released, students. Now what happens over here? You can also write heat released. If I talk about the general reaction, if I take general reaction of alkane, what it would be? CnH2n plus 2. Okay, this is going to be my alkane molecule, where I have to put the value of N as 1, 2, 3 according to the carbon atoms required. Then here I have to use 3n plus 1 by 2 in front of O2 to balance it out, students. Now what comes? It comes out to be NCO2 plus N plus 1 water. This is the general reaction. Just you need to write the number of atoms, like for N values, right? Now combustion is basically when used in limited supply. What is the reaction? When combustion is used in limited supply, when it is used in limited supply, what do we observe? See, when methane is reacting with O2, students, now CO2 is not formed. Here carbon is formed. Here carbon is formed plus water is released. Now this is basically used in the inks. This carbon is basically used in the inks. So this is the reaction when combustion is used in limited supply. Here you can also write limited over here. So this was all about combustion, chemical reaction. Now moving forward is our next reaction, that is the reaction with the steam. It is quite easy. See, when CH4 reacts with steam, now this is steam form. This is what? This is your steam form. Well, alkane molecule reacts with steam. It forms carbon monoxide. CO is formed and H2 is released. And H2 is released. Now, this is what? This is syngas. This is syngas. Kindly put a star mark over here because it is going to be the most important reaction. It is going to be very most important reaction, right? Okay, students. Now proceeding towards our next reaction, that is aromatization. Now what is aromatization? The formation of aromatic ring. From your open chain, you need to form a closed chain. That means an aromatic chain. And for this, you at least require carbon atoms to be at least 6. N value should be at least 6 or more than 6, not below 6, because then aromatic ring will not be formed. So if I take the case of N-hexane, if I take the case of N-hexane, that is CH3, CH2, 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 CH3. Let us count the number of atoms. 1, 2, 3, 4, 5, 6. This is N-hexane, my dear students. This is what N-hexane it is. Now, it occurs in the presence of various reagents, you know. One of the reagents can be V2O5, Cr2O3 or Al2O3. You can take two in the pairs, okay? Take either of these two in pairs, and it occurs basically in the presence of, again, 773 Kelvin near about, and you obtain what? An aromatic ring. You obtain an aromatic ring, students. Benzene is formed over here. Benzene is formed over here. Clear? Okay. Now comes, students, our next reaction. This next reaction is basically isomerization. Isomerization. So, you know, during the start of organic chemistry, we did IUPAC. Then we did basically isomerization. I have already explained you what are isomers, students. Isomers are those organic compounds which have same molecular formula but at least one different property. Now what we are going to do over here is that we are going to take any of the alkanes and we are going to obtain different alkanes, but we are going to obtain isomers of that. How come? Let us take of hexane only. CH3, CH2, 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 CH3. Now, I guess all of the students would be able to answer this question in only few seconds. Just the thing they need to remember over here is the reagent that you need to here use is anhydrous, AlCl3 and HCl, students. So, if I take anhydrous, okay, anhydrous AlCl3. If I'm going to take anhydrous AlCl3 and HCl over here, so what I'm going to observe is I'm going to make its isomers. So what will its isomers? See, I can make this of 5-membered CH3, CH2, CH2, CH2. Here CH will come, then here CH3. Is it an isomer of this? Yes, for sure. One more isomer that we can obtain over here is CH3, CH2, CH, CH3, CH2, CH3. We can also obtain this isomer, students. So this is what? This is isomerization case. Clear? It is very easy, students. Now comes our next reaction. So students, as we were doing pyrolysis and cracking, let us take one example to understand it a bit more. If we take CH3, CH2, CH3. And now we are going to do basically two steps over here. One is going to be dehydrogenation and another one that is going to be cracking. When I'm going to take the very first step, what I'm going to obtain over here is that I have to break the bond between carbon and hydrogen. So what I'm getting over here is CH3, single bond CH, double bond CH2, right, plus H2, because I am going to break the bond between carbon and hydrogen. I'm going to break between these carbon and hydrogen and between this carbon and hydrogen. And the another one is cracking. In cracking, what we do? We break the bond between carbon and hydrogen and also in between what? Carbon and carbon. So here what I am going to get? I am going to get CH2 double bond CH2, students, plus what I'm going to get? I'm going to get CH4. Now students, it was all about pyrolysis and cracking. Now we will move forward towards our next segment, that is alkenes. If I talk about alkenes, alkenes are basically the unsaturated hydrocarbons, right? What do we observe over here? We observe that carbon contain a double bond over here in alkenes. And other than this, students, alkenes are basically referred as olefins. Why they are referred to as olefin, students? Because the very first member of the alkene family, the very first member on the reaction with chlorine produced an oily substance. The very first member of this family. Okay, now students, if I talk about the general formula, it is CnH2n students. The general formula for alkenes is CnH2n. In alkenes, what do we observed? CnH2n plus 2. Here, what are we getting? CnH2n. Clear? Now, students, we are going to see the methods of preparation of alkene. And if I talk about the very first method, it is going to be hydrogenation. What is the very first method? The very first method is hydrogenation. Now what happens over hydrogenation? We are going to use a reagent over here. Now what are these reagents, students? What are these reagents? We are going to use here Lindlard's catalyst. What we are going to use over here? Lindlard's reagent or catalyst, you can say. Now what happens over here? How it is made, what is the combination? We are going to take a poison catalyst over here, which is going to do what? Now there are basically various kind of catalyst, one which increases the rate of reaction and another which decreases the rate of reaction. What are the reagents? First of all, let me tell you, the reagents are H2, okay, plus this we are going to get over here palladonized carbon. Now this basically palladonized carbon is poisoned by sulfur or quinolone. It is poisoned by sulfur or quinolone. Why this happens? Students, why does this happen? It happens because whenever we are doing hydrogenation reaction, what we are going to observe, we are going to get our product alkene, and we have already seen in the reactions, what we have seen, that basically if we have this alkyne with us, then in the presence of nickel, platinum, palladium, what do? We take hydrogen atoms and we do the attack of hydrogen atom over the carbon atoms, right? So what do we get over here? We get an alkene molecule. Then further this reaction proceeds, and again one hydrogen is attacking the another one, and we are getting what? We are getting our alkanes. We are getting what? We are getting our alkanes. So students, we know that we want to produce alkene, but we are getting what? We are getting our alkanes. To stop this reaction at this point, we are using the poison catalyst, which is going to stop this reaction over here. And when it is poisoned by sulfur or quinolone, it is basically the Lindlard's reagent. It is basically that. Now students, okay, as I have told you, we need to stop it at what? Alkene. So for that, we have taken this catalyst. Now in the given reactions, what you are going to get? This is your alkyne. This is your alkyne, and H2 is going to react over here. Now you have taken this. To poison it, you have taken sulfur as well as with you, or quinolone. Now what you are getting here? You will get over here the cis product. You will obtain the cis product over here. Do remember this. Do remember this. You are going to get cis product. I am also taking one of the example. If you have this as your alkyne molecule. Okay. Now this will not proceed further because we have used the poison catalyst. Now this is with you, or other than this, you can also see BaSO4 is also present here. Now you are going to get what? A cis product. In the cis product, see, you are going to get an alkene, you know that. You know that. Now both the hydrogens will be present on the same side to obtain what? A cis product. Now what is happening over here? This H2 students, this hydrogen will attack over here, another hydrogen will attack over here, and this bond will break. This is the basic process that we did during the formation of alkanes. It is the same process that we are doing over here. What is the same process? We need to break the double bond, and then we need to attack the hydrogen over there. But during the formation of product, do remember we are going to get a cis product, and in the cis product, both the hydrogens are going to be in the same direction, students. This point is the most important point. And what have we used over here? We have used over here H2 and PD carbon. Palladonized carbon, and it is poisoned by sulfur quinolone. Why? Because we need to stop this reaction over here, otherwise this H2 is going to attack again and will produce an alkane molecule, but we didn't want that. Now students, this was the formation of cis. Now to obtain a trans product, which of the following reaction we are going to do? We are going to do bridge reduction. In bridge reduction, we are going to get the trans product. We are going to get the trans product. Again, we are having an alkene molecule. Let us say we are having R dash C triple one C R over here. Again, this reaction is happening. Now, this reaction should happen in the presence of sodium and NH3. Do remember this. To obtain a trans product, you need this reaction to occur in the presence of sodium and NH3. Right now, what is going to be happening over here? What is going to happen over here? You know that H2 is going to attack over here from this side or from this side, and this double bond is going to break. Now, to obtain the product, you are going to see that R dash is present over here, R is present over here, hydrogen is present over here, and another hydrogen is present over here. Clear? So this is what? This is our trans product that we obtained. Clear? For cis product, it was very simple. You used PD carbon and it was the Lillard's reagent. And for, the trans product, you did Birch reduction. Now comes the next method of preparation, students. For next method of preparation, that is dehydration of alcohol. If I talk about a dehydration of alcohol, what we are going to do? We are going to take an alcohol, that is ROH, and we know that we have to obtain our product, that is alkene. It will be done in the presence of concentrated H2SO4, H3PO4 or H positive, right? And we are going to obtain our alkene from this side. We are going to get our alkene. Now, what happens over here, students? What happens over here? See, this ROH, basically, when it reacts, there is an electrophile, that is H positive, that is working from H2SO4 or H3PO4. Then this OH basically has lone pair of electrons which attack over the H positive. And what do we get over here? We get over here ROH positive. We are getting this substance now. Now what happens over here? Here water molecule liberates out. Here this water molecule liberates out and we get our carbocation, that is R positive. Now this carbocation, students, this carbocation can either do rearrangement. It can either work on rearrangement. And if it's not doing any rearrangement, then directly, students, hydrogen will come out. Directly H positive will come out and will lead to the production of alkene. So the main part over here is the rearrangement. In some of the cases, you are going to see rearrangement is occurring. In some of the cases, you are going to get where rearrangement is not occurring. So what I'm going to tell over here is that dehydration of alcohol contains what? We are going to, dehydration refers to what? See, we are using concentrated H2SO4 and H3PO4. That's it. And with the help of alcohol, we are obtaining alkene. So now let us see the rearrangement one task. If I take hydride shift, it is an example of rearrangement. If I talk about hydride shift, students, let us take one example where I'm going to tell you hydride shift refers to as the H positive shift. Now, what is going to happen over here? I told you that R positive is being generated from the ROH, right? We have seen this case now. Let us take this example, CH3C. CH3. Here, students, we want R positive. So let me say that there is no CH3 over here. Let us say there is a hydrogen over here and there is a positive sign over here. We have this with us. Now what happens? You know that this carbon has basically 4 valency. That means it has a hydrogen with it. And you know that this is 1 degree carbocation, but you know that 3 degrees more stable than 2 degree than 1 degree. So what will happen over here? This hydrogen will take its electron and moves towards the CH2 positive and will break this bond between carbon and hydrogen, leading to the formation of CH3, C positive, then comes H over here and then comes CH3 over here. Why CH3? Because this hydrogen is attached to this CH2 forming CH3 and this bond is broken over here. Electrons are moved from the carbon away from the carbon. So carbon doesn't have any electrons, so hence it is positive. Now this is what? This is the rearranged product. And the next step is what? Next step is just you have to remove one hydrogen. If you'll remove this hydrogen, there will be a double bond between this and an alkene will be formed. Clear? Okay, now comes from vicinal dihalide. What do you mean by vicinal dihalide? Dihalide refers to two halogen groups and vicinal dihalide refers to like this. when the adjacent carbon atoms have the halide groups with it, that is the vicinal dihalide. This reaction is now going to occur in the presence of Zn students, in the presence of zinc, and with 300 degrees Celsius, with 300 degrees Celsius. What you are going to observe over here is that now this Zn will react with this X2, and these two bonds will break over, and there will be a double bond between these two, leading to the formation of alkene molecule, plus Znx2 is liberated over here. Now to complete the valency of carbon, other hydrogens are attached with it. So it is very easily. See, this is the vicinal dihalide. If I talk about geminal dihalide, what do you mean by geminal dihalide? See, if I talk about geminal dihalide, then we will see that only a single carbon atom contains two halogen groups. That is geminal dihalide. But in vicinal dihalide, we see that the adjacent carbon atoms, that the adjacent one contains two halogens. If halogens are present on the single carbon, then they are referred to as geminal. But if it is present on, the single carbon atom, here S will not come, then it is known as vicinal dihalide. Clear? It is clear. Here you can see Br also, then Z and Br2 will be released. This is the formation of alkene. Now comes next method of preparation, which is the most important, that is dehydrohalogenation. Dehydrohalogenation, what do you observe over here? It is basically beta elimination. Here you will see that halogen will come out from the reactant. How it will come out? See, if I see this is my reactant, and halogen is attached over this carbon atom. So this carbon atom is alpha carbon, and the carbon next to the carbon is known as beta carbon. If it is beta carbon, then it is referred to what? It is referred to beta hydrogen. So here what you are going to see, beta elimination, that means beta hydrogen will be eliminated. Also, what will be eliminated? Alpha halogen. So two things that you are going to observe over here are going to eliminate, that is beta hydrogen and alpha halogen. Now let me tell you students what is happening over here. First of all, identify alpha carbon. How you will identify? The halogen that is attached to the carbon is alpha carbon, and the carbon next to the alpha carbon is beta carbon. The carbon which contains hydrogen with it, the beta carbon, that will be referred to as beta hydrogen. Now when this will be removed and this will be removed, there will be a double bond between both of these. There will be a double bond, and we are going to get this alkene as a product. We are going to get this alkene as our product. Clear, students? And this now hydrogen will react with this halogen and will be forming HX over here. Okay, this is the basic reaction. Now the rate of reactivity is the order. This is the order for rate of reactivity. What? That the rate for here, if I talk about alkyl fluoride, it is very less. Why it is very less? Because fluorine is most electronegative. It has electronegativity so high that this bond is so strong that it is unable to break. That's why here we need to break this bond, and whose bond will be broken? Who have less electronegativity, so that it can be easily broken. So Ri has basically more rate of reaction. Why? More rate of reactivity. Why? Because this bond can easily be broken, while RF bond takes a lot of time to break, because it is a strong bond, because there is a lot of electronegativity due to fluorine atom. Now students, here no intermediate formation occurs over here. Other than this, students, only transition state will be formed. So do remember this. It is the most important reaction that will come in your examination. If we see examination point of view, it is beta elimination reaction. Clear, students? Okay. If I talk about the properties of alkene, now comes the properties of alkene. We have seen what? We have seen the preparation. If I talk about the properties, the very first property is that first 3 members are gaseous in nature. Then the next 14 members basically are liquid, and higher ones are solid, just like in the alkanes case, right? Other than this, they are slightly polar than alkanes. Why they are slightly polar than alkane? Because here you see there is a double bond between the carbon atoms, and if I see the hybridization over here, it is sp2 hybridized. This carbon is also sp2 hybridized. Due to the sp2 hybridization, we know that electronegativity directly depends upon the s character. More the s character, more is the electronegativity. So here what we are observing, that these are, if there is a difference in the electronegativity, poles arises which lead to the formation of polarity. So what I'm telling over here, that due to in alkanes what we observed, there was carbon and hydrogen. They almost have electronegativity same. So they were non-polar in nature. But if I talk about alkenes, due to the increase in s character, electronegativity got increased, and due to the increase in electronegativity, poles arise, which lead to the formation of polarity. So it is more polar than the alkanes. Now if I talk about the color and the odor of them, the ethene is colorless, but it have a faint sweet smell, but rest of the molecules are colorless and odorless. If I talk about boiling point, they have low boiling point, but if the number of carbon atoms increases, the boiling point will increase. So yes, due to the non-polar nature, they are insoluble in water. Now students, comes the first chemical property, that is addition of hydrogen. This you have already done. Chemical property is addition of hydrogen. Now if I talk about addition of hydrogen, let us take this case, and we are going to add hydrogen in the presence of nickel, platinum or palladium. We have also done in the previous case. What we are going to do, we are going to break this bond, and one hydrogen will attack over here and one will attack over here. So this you will get as your byproduct. Clear students? Other than this, let us take one more example. If I take this example over here, now again what you are going to do over here, this is occurring in the presence of nickel, platinum and palladium. Here also you are going to break this double bond, and when this double bond is going to break, one hydrogen is going to attack over here and another here. So you are going to get this as your product. You are going to get this as your product. So this is basically what? This is basically a chemical property of alkene, in which from alkene we can obtain what? We can obtain the alkane molecules. If you remember, in the alkanes we have studied the preparation of alkanes from the alkynes, from the alkynes. Then we have also seen the preparation of alkane from the alkene molecule. If you remember there, that I told you why it is happening in the presence of nickel, platinum or palladium, because here nickel, platinum, palladium is basically a catalyst, and here there is a adsorption process. Which process occurs over here? Adsorption occurs. And what happened in adsorption, students? In adsorption we saw that it is a surface phenomena. When it is a surface phenomena, the H2 molecule comes towards the surface of the nickel. Now I'm not making the mechanism again and again, because we have already done in the alkane case, right? So when the H2 molecule comes over the surface of the nickel, then it does the interaction with the alkene molecule, and the bond gets break, and we obtain the alkane as of a product, and the catalyst comes out, right? So this was the first chemical property, that is the addition of hydrogen, students. If I talk about the next chemical property, it is addition of halogen. It is addition of halogen. Addition of halogen. Now if I talk about addition of halogen, let us take this case RCH double bond CH2, and we are going to add any of the halogen. For example, I'm taking X as our halogen, and this X can be fluorine, chlorine, bromine, iodine, and it occurs in the presence of what? CCl4. So what we are getting over here, we are getting a product that this double bond will break over, and yes, one X is going to attack at this carbon and one X is going to attack at this carbon. So this leads to the formation of this, right? This leads to this formation. Now it is also referred to as a test for unsaturation. Why? We can also calculate the test for unsaturation if you are going to use Br2 over here instead of X2. X2 can be fluorine, chlorine, bromine, iodine. So if you are going to take, it is RCH double bond CH2 plus Br2 in the presence of CCl4. So what you are getting over here, the double bond is going to break over, and yes, you are going to get this as a product, right? Now students, what happened? This Br2 basically is reddish brown in color, but when we are getting this as a product, this product is basically what? It is an alkane. Now if it is an alkane, the color, if the color becomes colorless, first it was reddish brown when we add Br2 in it, but when the color become colorless, then this is a test for unsaturation, that the reactant which we used to check it is unsaturated or not, it is unsaturated because the color has changed. So from reddish brown color, students, from reddish brown color, what do we got? We obtained a colorless substance. We obtain a colorless substance. So this is a test for unsaturation that will be coming in your examination. It is asked many a times, right students? Now other than this chemical property is the addition of a hydrogen halide. Now what do you mean by hydrogen halide? Addition of, now see, if you have done alkanes, no, then alkenes and alkynes are very simple for you. Now you will feel that these reactions are very much easy. If I talk about hydrogen halide, it is HX. It is what? It is HX. HF, HCl, HBr, HI. And if I talk about their order, basically what happens again? HF then we have HCl, then we have HBr, then we have HI. This is the order of reactivity. Why? Again, because here fluorine is most electronegative. Due to the more electronegativity of fluorine atom, this bond is very strong and it will not break because it has more electronegativity. And we want the addition of hydrogen halide, so we will break the bond. If I talk about the symmetrical alkene, if I talk about this symmetrical alkene, and I'm going to do a reaction of HBr over here, so what I want that this bond is going to break and also this double bond is going to break. So to break this bond, either we are going to take HCl, HBr or HI, but we are not going to use HF. Why? Because it is, very strong bond, right? Now what we are getting over here, if it is symmetrical, then you can either attach hydrogen over here or over here. It is the same thing. So I am attacking hydrogen over here and Br over here. What I am obtaining over here, I am obtaining CH, and yes, there are two more bonds over here and single bond over here. Then we are obtaining Br over here and there is a hydrogen over here like this, right? Clear? Now, but if we get an unsymmetrical, if we obtain any unsymmetrical, but before this, let us take one more example over here. If I talk about CH3, CH, double bond CH, CH3. Okay, now in this case, again, I'm going to take HBr and I want you all to write the answers in the comment section. I want you all to write the answer in the comment section. It is quite easy, just similar to this. You can do any of the things, either get hydrogen attack to this carbon or to this carbon, or attack Br to this carbon or to this carbon. It is the same thing, students. Why it is the same thing? Because it is symmetrical. How you can check the symmetrical? See this from the double bond. It is same on both the sides, right? I want the answer in the comment section with your name, students. Okay, now if we take the unsymmetrical one. Now if we take the unsymmetrical one. In unsymmetrical one rises Markovnikov's rule. Now, what is the unsymmetrical one? Let us take this case: CH3, single bond CH, double bond CH2, and I am taking HBr over here. I want my product. So you know that this hydrogen halide is going to break, yes, and both of these are going to attack. Now, which will attack on which? See, if hydrogen is attacking on this carbon atom, then what we are going to get? CH3, CH2, CH2Br. How come? See, if hydrogen is attacking on this carbon, then Br is attacking over this one. We are getting this as of a product. But if hydrogen is attacking, one second. If hydrogen is attacking now on this carbon and Br on this, then what is the another product that we get over here? CH3, CH, BrCH3. So we are getting two products over here, but the question arises which is in the more quantity. So this is in the more quantity. It is referred to as a major product because it is more stable, while this is the minor product. Now, how come I got to know that this is the major product or this is the minor product? It is because of the Markovnikov rule. It is because of the Markovnikov rule. Now, what is Markovnikov rules? The question arises that the negative part of the hydrogen halide or the negative part of the attacking reagent is going to attack on the reactant. On which carbon atom? The carbon atom which have least number of hydrogen atom. Negative part will attack on that carbon atom, of alkene which has least number of hydrogen atoms. It is most important. Do remember, in Markovnikov we are going to see the least number of hydrogen atom, but in anti-Markovnikov we are going to see more number of hydrogen atom. So this is the process that occurred over here. Let us see once again. See why it is major, because the negative part, that is the Br negative, attacked to that carbon atom of the doubly bonded which has less number. It has one hydrogen, it has two hydrogens, so it has less number of hydrogen. So Br negative is going to attack on this carbon atom. Hence this is the major product, right, students? Okay, now students, okay, now moving forward towards the next chemical property, that is the addition of sulfuric acid. Now comes what? Addition of sulfuric acid. Now, these are the basic, chemical reactions. You just need to practice once or twice, right? If I'm taking again CH3CH double bond CH2. Now I want the addition of sulfuric acid. That means H2SO4 addition will be done over here. Now if H2SO4 addition is happening over here, now do remember here you have H positive ion with you. Here what you have? H positive with you and HSO4 negative with you. So you are going to see the negative part is going to attack to which carbon atom which has less number of hydrogen atoms. This is the Markovnikov rule. So this will attack over this because it has less number of hydrogen. So what we are getting over here? CH3C. Here now see this CH3C, now double bond is broken over here. We are going to get HSO4 over here. Now again single bond because double bond is gone. Now also H is also present with this carbon atom, and now this H positive will attack on this carbon atom, so it will get CH3. So this is the product that we are getting over here. The mechanism that is working over here is Markovnikov's rule. Again I am repeating, it is the one that is Markovnikov's rule, which states us that the negative part will attack on that carbon atom which has least number of hydrogen atoms. Do not get confused in this. Whenever you are getting an unsymmetrical alkene, kindly attack the negative part over it. Here negative part is HSO4 negative, so it will attack on that carbon atom which has less number of hydrogen. If I talk about only, yes, do remember here we are not going to observe this carbon atom. Why we are not going to observe this carbon atom? Because this is the chemical property of alkene. What we are doing here, we are observing on the alkene. That means we are going to observe on the double bond portion. Clear? So we are going to observe these carbon atoms. Now comes the next important chemical property, student, that is ozonolysis. Now, this is the most important. In ozonolysis, there will be addition of ozone, that is O3. Again, I'm going to take an unsymmetrical one, that is CH3, CH, double bond, CH2. And there will be an addition of O3. Now, what happens over here? Do listen very carefully. See, there will be 3 oxygen that they are going to attack. And they are going to attack on this alkene first of all. So, what will happen over here? This is CH3, this is the carbon atom. And this double bond will break over and one oxygen will come in between both of these. This CH2 will remain as it is. Now, one oxygen has came in between, 2 oxygens are still pending. What will happen over here? 1 oxygen, 2 oxygen, and like this. See, it is a quite different thing that you are observing over here. Now, if you'll complete the valency of this carbon, it has a hydrogen over here also. What I have done the attack of O3. O3 on this doubly bonded. Now, this doubly bonded is going to break, and in both of these carbon atoms, 1 oxygen is coming on the top and other 2 are coming together. Right, students? Now, what is the very next step? Look very carefully. What will be the very next step? In the very next step, students, this is going to break. What you're going to get over here? CH3. See over here, this CH3 is written as it is, this CH is written as it is, and there will be a double bond between this oxygen because it is going to break. Other than this, what you are going to get over here? Other than this, this will break. Other than this, this will break. And what we are going to get over here is, if you see, it is a CH2. Again, it is CH2 and this with a bond with oxygen. So what we will see? CH double bond oxygen. Clear? So this is the most important reaction, students. It can be asked in your examination, ozonolysis. And yes, in 12th standard also you are going to study this. So what I've done, it is very simple. There is attack of O3, and O3 attacks in such a situation that there will be 1 oxygen between the doubly bonded carbons atom. This double bond will break and 1 oxygen will come in between these, and the other 2 are going to come together. Clear? Now comes the last chemical property, that is polymerization. That is polymerization, students. In polymerization, what do we see? We are obtaining a polymer with the help of a monomer. Basically, the small unit monomers join together to form a polymer. Now, if I talk about this alkene, that is CH2 double bond CH2. This is my monomer. Here I am writing N. N here refers to as number of monomers. Now, when the polymerization process occur, it leads to the formation of, a chain-like structure. This double bond will break. It will come like CH2, single bond CH2, and will move like this. So this is what it is, a polymer. It is what it is, a polymer. Now let us take one more case over here. If I see CH double bond CH2 and I have CH3 with me, this is my monomer now, N times monomer. So what I'm going to get? A straight chain I'm going to get. CH. Now this double bond is going to break CH2. It is going to make a bond further. Here this CH3 is attached, and this is the polymeric chain. This is the polymeric chain. So basically what do we do? From with the help of monomers, these n number of monomers will join together to form a straight chain like structure, that is the polymers. And polymers in the everyday day-to-day life has the most important uses, students. So I took two of the examples. I took very first example of two carbon atoms, the very first simplest alkene, I would say. Okay, now this is again the monomer, n times of this alkene ethene molecule, okay, formed this polyethene for us, right? Where all the double bonds will break out and will lead to the formation of the single bonds. And if I talk about the next case, students, in this case we have seen this is the propene, right? Three carbon atoms, propene. Now this propene monomer is taken and which lead to the formation of what? Again a polymer. Again a polymer. So students, this were the chemical properties of alkene. Clear? These were interesting and I want you all to practice it more and more. Okay, now students, comes our next segment, that is the alkynes one. If I talk about the alkynes one, basically alkynes are what? They are unsaturated hydrocarbons. They are unsaturated hydrocarbons, right, students? And you know, they are highly reactive. They are highly reactive. They are highly reactive ones. And if I talk about more about alkynes, they have a molecular formula of CnH2n minus 2, students. If I talk about alkane, they had CnH2n plus 2. If I talk about alkene, it had CnH2n. If I talk about alkyne, they have CnH2n minus 2. And if I take the very first case of the alkyne, that is for second number of carbon atom, the very first member is when n value is 2. So we are going to get what? C2H2. C2H2. This is we are going to get, and it is ethyne, which is gaseous in nature. It is ethyne. Ethyne, which is gaseous in nature, students. Okay, this one is gaseous in nature, also known as acetylene gas. Also known as acetylene gas. So you can also write the n values 3, 4, 5 to obtain the other products. If you put the n value as 3, what you are going to get? C3. You know, 3 into 2 is 6, 6 minus 2 is 4. So C3H4. Then is the next member. Then you are going to put the n value as a 4. C4H6. Clear, students? So likewise, you can form all the homologous series for the alkynes. Now, students, we will move forward towards our next topic. So yes, students, now comes our methods of preparation of alkyne. How do we prepare alkyne? So our first method is from calcium carbide. See, first of all, what happens? Calcium carbonate is taken, which is CaCO3, and it is heated and we obtain calcium oxide plus CO2. Now, the very next step is CaO, that is calcium oxide. It reacts with 3 carbons forming calcium monoxide and calcium carbide. Now, with the help of this calcium carbide, students, we are going to get our alkyne as our product. Now, how come? This calcium carbide, which is C2, it reacts with water molecule, leading to the formation of calcium hydroxide plus our ethyne. Now, from here, ethyne is obtained. How come? See, there are basically what? It is H2O. So I can write H2 as HOH, HOH. Now what happens over here? This Ca combines with this twice of OH, forming CaOH2. And what is left now? We are left with 2 carbons and 2 hydrogens. So this forms what? Ethyne, which is basically our what? Alkyne. So this is the formation of alkyne, very first method. The next method is vicinal dihalide. Again, I've told you what is vicinal, when the 2 adjacent carbon atoms contain the halogen groups, right? So it has Br with it, the 2 different halogen groups. Now what happens here? Alcoholic KOH is used. Do remember, students, do remember, aqueous KOH will not be used over here. Alcoholic KOH will be used over here. And well, alcoholic KOH basically reacts. What happens over here? What happens? Now this Br from here, again the process, you remember this carbon atom attached to the halogen is alpha, the carbon next to it is beta, it has hydrogen over here. So there what will happen? This halogen of alpha and this hydrogen of beta is going to eliminate. It is going to eliminate and there will be bond formation between both of these. And now in the next step, when we are obtaining an alkene molecule by beta elimination, by the elimination of alpha halogen and beta hydrogen, we obtain an alkene molecule. But now what will happen? Now in the presence of sodamide, students, NaH2, NaH2. This again this Br is going to remove and this hydrogen is going to remove. Now again HBr removal will be there. See, sodamide is used for the formation of removal of our halide, hydrogen halide. So HBr is removed and again a triple bond arises, which leads to the formation of what? It leads to the formation of alkyne. It is the most important vicinal one, right? Okay, now students, moving to the physical properties of alkyne. If I talk about the physical property, the very first property is that first 3 members of alkyne groups are gaseous. Okay, the next 8 members are liquid, and the next one after the 8 one, first 3, then the 8, and then from, I guess it's like from 13th or 14th member, they are going to be the solids one, right? So you need to remember first 3 gaseous, then liquid, then solid, just similar to the alkenes and the alkane ones, right? Now students, if I talk about the next physical property is that it is colorless. Do remember this. Other than this, all are odorless. Okay, and if I see it's weakly polar, we have seen the polarity. The polarity arises due to the S character over here. There is a 50% S character in the alkynes case, due to which electronegativity difference arises, and the more the S character, more is the electronegativity. More is the electronegativity, that means more the poles will be arised. So if we talk about the alkanes case, they were non-polar. Why they were non-polar? Because there was no S character over here. There was very less S character. And if I talk about alkanes only, the electronegativity of alkanes, the carbon and hydrogen was always similar. So there were no poles. But if I talk about alkenes or alkynes, we see that the poles arise because the nature of the double bond or the triple bond, due to which the S character got increased. And when the S character got increased, the polarity came, right? Now students, other than this, they are immiscible in water, but yes, they are soluble in benzene like solvents, right? So these were the physical properties, students, that you need to keep in your mind. Okay, now moving forward to the chemical properties, I want you all to remember the preparation methods again. So I'm going to repeat the preparation method, because these we have seen alkanes, there are a lot of preparation methods. In alkenes there are preparation method, but in alkyne there are only 2 or 3 preparation method that you need to keep in remember in your mind. The very first is calcium carbide. In many of the books, directly this reaction is given to you. So I have given you all of the steps. From the calcium carbonate CaCO3, you are obtaining this calcium oxide plus CO2. Then you are obtaining this, that calcium oxide plus 3 carbon. You are getting calcium monoxide plus calcium our carbide. Now this is very important. How calcium carbide is formed, this you should know. Okay, then it will react with water, leading to the formation of alkyne. Other than this, students, what is happening over here? Vicinal dihalide. More important, very important, because we are not taking germinal dihalide. In germinal dihalide, it won't take place because we want alpha halogen and beta hydrogen. Do remember this. Why we are not taking germinal one? Because in the germinal one, what we observed, you observed that the same carbon atom is having the 2 halogen groups. But during the beta elimination, we want beta hydrogen that should be eliminated. So that's why we took the vicinal one. And the vicinal one, again, I'm going to write over here, beta elimination. From here, if I see over here, alpha halogen and beta hydrogen is eliminated. Do not forget this, because it is going to help you in alkynes case also and in alkenes case also. In both of these cases, it is going to help you out, right, students? Now we have seen the physical properties. We have compared the properties with the alkanes and the another one also. Now we will see our what? We will see our chemical properties, students. If I talk about the chemical properties, see, alkynes is very small topic. It's not a big deal. If I talk about the chemical properties, students, in the chemical properties, they are acidic. They are acidic. How they are acidic? See, they are acidic. If I talk about alkanes and alkenes, they are not acidic as alkynes. Why they are acidic, students? Because when there was a reaction of alkyne with sodium metal, or when there was a reaction of alkyne with NaNH2, when alkyne reacted with NaNH2, the reaction occurred. The reaction occurred. And also, when alkyne reacted with sodium metal or any another metal, again this reaction occurred. Again this reaction occurred, students. When it reacted, there was a salt formation over here, and there was H2 that was released, which explained us, these two reactions explained us through experiments that yes, alkynes are acidic in nature. That's why they are making here a salt when it reacted with metal, or when it reacted with any NH2, the reaction occurred. But if I talk about alkenes and if I talk about alkanes, they are not acidic in nature. Do remember this. And due to this, now if they are acidic, what are alkynes going to do? Observe this. If they are acidic, students, if they are acidic, then what will happen? See, we know that yes, there is a s character in these carbon atoms more arised. Why? Due to the triple bond here. Now what do we observe? The hybridization. If I talk about hybridization, there are two sigma bonds. See, whenever you are having four sigma bonds, here is sigma bonds plus lone pair sum. So if there are four sigma bonds, then the hybridization is sp3. If it is 3, then the hybridization is sp2. When it is 2, it is hybridization is sp. So over here there are two sigma bonds, other the are pi bonds. This one is sigma, this one is sigma, right? Other are pi bonds. So two sigma bonds, that means hybridization is sp. Here also hybridization is sp. Now due to sp hybridization, they have the electronegativity difference, because more the s character, more the electronegativity. And when the carbon have more electronegativity, what it will do? It will break this bond, it will break this bond, will contain negative charges over here, and yes, these protons are going to release, these protons, this H positive are going to release, which states us what? That they are acidic in nature. Now what happens? Let us take one example. We have this as our reactant, and I tell you that kindly reacted with sodium. So what you're going to do, it is going to be a substitution kind of reaction. This hydrogen will come out because it is acidic in nature. This H positive will break out, and this sodium will take its place. So what we are going to get over here is, we are going to get this as our structure, and yes, H2 will be released. And to balance it out, half H2 will come, because you know H2 when released will be released in the form of gaseous also. Now again, I'm going to react this molecule which is obtained as our product with Na, again with Na. Now what will happen? Now this bond will break, and this, now Na will attack at this carbon atom. So we are going to get Na carbon, triple bond carbon, Na, and again H2 will release. Okay, so if I write the overall reaction, students all over here, if I write the overall reaction, what I'm getting, my alkyne, I have reacted it with 2 Na, leading to the formation of what? Na, single bond carbon, triple bond carbon, Na. Clear students? And also now complete H2 will release. Half H2 plus half H2 gives 1 H2. Is it clear to you? Is this chemical property clear to you? Now, how we got to know that this is the chemical property? Due to its acidic nature. Acidic nature. They ask you these types of reactions in the examination. Now, if you know both of these steps, it is quite simple for you. You know that H positive, that is the proton, is going to release out. When proton is going to release out, sodium is going to take its position. Now, sodium metal, when reacted, will takes its position and will lead to the formation of this. First of all, this bond is going to break, or either you can break that bond. It is the same thing, but the bond between an carbon and hydrogen is going to break. Why? Because they're acidic in nature, right, students? Other than this, they do addition reaction. And if I talk about addition reaction, let us take one case. Generally, I'm talking about addition reaction in the chemical property. When I say carbon, triple bond carbon is present, and yes, it reacts with HZ. Let us say that Z here is more electronegative. Now, when it is more electronegative, then what will happen over here? It will arise a negative charge. It will arise a positive charge when it is going to break, right, students? What is going to happen? Now, this H positive is going to attack on the carbon atom, and yes, its bond is going to break. Its bond is going to break. When its bond is going to break, what is happening over here? It will, this bond is broken. Kindly correct this arrow. Okay. This H positive is attacking. Now, when this H positive is attacking, the electrons are moving. When the electrons are moving from one direction, what happens over here? This hydrogen is attached over here. This bond is broken and it is electron deficient, so arises with a positive charge. Now, what happens over here? Z negative is also produced. Now, this Z negative will attack on what? C positive, leading to the formation of this as our product. It was quite simple. It is a general reaction. That addition occurs how? First of all, the triple bond is going to break and the electronegative part comes out, separates out, and yes, the H positive attacks. And when the H positive attacks, yes, the carbocation is formed, and then the Z negative will be attacking on the carbocation, leading to the formation of our product. Right, students? In addition reaction, there are various cases that we will study just right now. So let us take the very first case for the addition reaction. So yes, students, now we are going to see the addition reaction properties only, that is the addition of dihalogen. Addition of dihalogen. Now what happens in the case of dihalogen? Two halogens are going to attack and they're going to add over the alkyne molecule. Now if I take the simplest alkyne, that is ethine, and I want here dihalogen, let us take Br2. Okay, now if I'm going to take Br2 over here, I want its addition. Now what is the basic step? It is going to occur in the presence of CCl4. First of all, do remember this. Now we know that when Br2 is going to attack over here, we know that it is symmetrical, so this double bond is going to break. One Br is going to attack and another one is going to attack on this carbon. It is quite a easy process. So what will happen over here? Hydrogen carbon double bond will be still present because triple bond is being broken. One Br is added over here, another Br is added over here. Now in the next step, what is going to happen? Again, in the presence of Br2 CCl4, it is going to happen. Again, this Br is going to attack on these carbon atoms, students, and this bond is going to break. So carbon, single bond carbon, hydrogen, Br, 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 hydrogen. Yes, this is the basic reaction of, dihalogen. Similarly, you can do the addition of dihydrogen. This also you have done. Addition of dihydrogen. If I talk about the addition of dihydrogen, what is occurring over here? Let us see. For the case of dihydrogen, this is my simplest molecule. It will occur in the presence of, again, what? Nickel, platinum, palladium. This you have already done, students, many a times. And this bond is going to break. It is going to attack over here. What we are getting? We are getting this as our structure. Now again, what? In the presence of nickel, platinum or palladium, it is going to occur, and this H2 is going to attack on both of these carbons, leading to the formation of what? Leading to the formation of what? Alkane. So these are kinds of, addition reaction that you should know. First, I told you about addition of dihalogen. That means two halogen groups are going to attack. And then I told you addition of dihydrogen. Then two hydrogens are going to attack over here. See, in the very first case and in the second case, they both have the similar steps. Now, these are symmetrical. If it comes out to be unsymmetrical, students, then what you need to do? You need to follow the Markovnikov's rule. What is the Markovnikov's rule? The negative part will move to that carbon atom which has less number of hydrogen atom. But do remember, students, when does the negative part moves to that carbon atom which has more number of hydrogen atom? When it is anti-Markovnikov rule, and it will occur in the presence of peroxide. So whenever you are given the the reagent on the arrow, the peroxide, that means you need to remember that here anti-Markovnikov rule is going to happen, and the negative part will move to that carbon atom which is going to have more number of hydrogen atoms. Is it clear to your students? Okay, now this ends our section for the alkynes. Now students, we are going to move further to the aromatic hydrocarbons. Now what are aromatic hydrocarbons? If I talk about aromatic hydrocarbon, they are also referred to as arenes, students. Okay, now in the aromatic one, we have already done in the GOC section also. What are the aromatic compounds? They are further classified into benzenoid and non-benzenoid. If you remember, aromatic hydrocarbons are further classified into what? Into benzenoid and the non-benzenoid ones. But in this lecture, in this chapter, we are going to focus more on benzenoid one. Benzenoid one are the ones which contain, they have benzene ring with them. They have benzene ring in them. So mostly we are going to focus on this only, the benzenoid one. Other than this, if I talk about benzene, students, benzene basically has a molecular formula of C6H6, which basically looks like This, students, you clearly know this, you have done in the GOC section also. It is highly unsaturated. It is what? It is highly unsaturated. And yes, for a compound to be aromatic, you should know that it should follow what? It should follow Huckel's rule. These all things we have already done in the GOC section, that is 4n plus 2 pi electrons. It should follow this 4n plus 2 pi electrons, okay, plus 2 pi electrons to be an aromatic compound, to be an aromatic compound. Other than this, it should be planar, it should be cyclic. These things we have already discussed over there. Okay, students, now we will see the preparation of aromatic hydrocarbons. So yes, my dear students, now let us see towards the methods of preparation of aromatic hydrocarbons. See, aromatic hydrocarbons can be prepared from alkynes, but not from alkenes and alkanes. So let us see, if I talk from alkynes, let us take the simplest one. This is my alkyne. I am going to take 3 alkynes over here. Now what happens, students? They are going to connect with each other in such a way that the triple bond between them is going to break. One triple bond is going to break, and so here what will happen? A single bond will come, which will lead to the formation of what? This structure. This structure over here. So this is what? This is our benzene. This is what? This is our benzene. So this is the basic reaction that we can do from the alkynes, which will be done in the presence of red hot iron tunings, right? This is going to occur in red hot Fe tuning. Do remember my point that from alkanes and alkenes you cannot obtain aromatic hydrocarbon. I will write over here, from alkanes and alkenes we cannot obtain this product directly. Obtain aromatic hydrocarbon. Clear? Is it clear to you, students? So this was the, I guess, very simplest method for you for the preparation of a benzene. Now, students, comes our next method of preparation, that is from phenol. If I talk about phenol, phenol is the one in which the benzene ring contains OH group. This is phenol. This is what? This is phenol. Now we need to prepare a benzene and we have phenol. So what we are going to do, the very basic reaction which we used to do again and again, is with Zn, that is zinc, is with zinc. We are going to heat it up in the presence of zinc. What we are going to get over here is that zinc will combine with oxygen, will form zinc oxide. It will form zinc oxide, that is ZnO, and our product, that is benzene, will be formed. You all will say, ma'am, where does hydrogen went? Hydrogen is still here. It is still here. These are still here. Is it clear to you? Is it clear to you? In the previous also, students, here I have shown carbon, carbon, carbon. If you want to show in the terms of carbon, this is the bond line notation. You can either show carbon over here, then you can show all the hydrogens also with them. Okay, it is the same thing. So don't get confused. You can either write in the form of representing each and every carbon atom, or either you can show with the bond line notation of the benzene ring. It is the same thing. Here I have written, here I've directly used phenol, and with the help of phenol we have obtained benzene. You can also open it and write in such a way. You can write in such a way also. You can write in such a way also, students. It is the same thing. It is the same thing. Don't get confused in these small things, right? Okay, so this was students' method of preparation from phenol, students. Now we will see the next method of preparation, that how can the aromatic hydrocarbons be obtained. Now, students, the next reaction can be decarboxylic reaction. In this, you are going to take sodium benzonate. If I talk about sodium benzonate, what it actually looks like. This is sodium benzonate. This is what sodium benzonate, students. Now it is going to react in the presence of NaOH. Okay. Also in the presence of calcium oxide. Now what is going to be happening over here? Na2CO3 will separate out and the product benzene will be obtained. Na2CO3 will separate out and we will obtain our product, that is benzene. That is the formation of aromatic hydrocarbon. So that is decarboxylic acid. Decarboxylic, not acid, decarboxylic reaction. Clear, students? It was quite easy, very simple. Now you can easily learn the formation of method of preparations of aromatic one, because these are basically 3 or 4 that you need to keep in your mind. Decarboxylic one, then the phenol one, and in the previous one, that the simplest one is the alkynes one. Is it clear to you? Now students, we will move forward towards the physical properties. Towards what? Towards the physical properties of the aromatic one. Okay. Now, if I talk about the physical properties, okay. If I talk about the physical properties, students, first of all, what we need to understand, they follow Huckel's rule. This you clearly know. Other than this, they are non-polar in nature. These are non-polar in nature, and hence you can see in benzene also resonance occur. Okay. These are colorless. Okay, you know what? You can compare all the physical properties and learn together. That will be easy for you. Now, students, they have a characteristic odor. For example, the naphthalene balls, right? So they have a characteristic odor. Characteristic odor. Example, the naphthalene balls. Clear? Example, the naphthalene ones. Now, if I talk about the physical state, basically benzene is liquid in state. But if I talk about the naphthalene ones, they are solid, right? Okay, for this it is liquid and for this it is solid. Either it can be liquid or it can be solid. Next is they are immiscible in water. Okay, but yes, they are soluble in what? They are soluble in benzene, you know. Now comes the next chemical properties. If I talk about the chemical properties, the very first chemical property that comes in our mind is electrophilic substitution of benzene. See what happens over here. Electrophilic, that means referred to as electron loving. Philic refers to as loving, electro is refers to as electron. Now, who will love electron? The one which has a positive charge, that means electrophile. That means electrophile. So now we will see the substitution reaction of the electrophile, that is the electron loving species. Now what will be substituted? Yes, the hydrogen from the benzene ring will be substituted by the electrophile. Now we will look forward towards the mechanism, students. First of all, we will look to the mechanism, and with the help of mechanism only we will learn the reactions. The very first is the generation of electrophile. Generation of electrophile. How electrophile is going to be generated? Electrophile is the one which is electron loving, which is going to attract electron towards itself. And to do this, we are going to use a certain catalyst. We are going to generate electrophile with the help of catalyst. Now this catalyst, students, is Lewis base. Sorry, this catalyst is Lewis acid. Sorry. This catalyst is Lewis acid, not Lewis base. Now, there are certain steps. For the electrophilic substitution reaction, the very first is generation of electrophile. That means electron loving species will be generated, right? Now this can be generated with the help of a catalyst, which is Lewis acid. Now basically generation of electrophiles we are going to see in 4 or 5 cases. Students, it can be nitration, it can be, sulfonation. One by one we are going to observe each one of them. The very first in which we are going to observe is chlorination. If I talk about chlorination, that means addition of chlorine, and if I talk about chlorine, it is going to be Cl2, that is ClCl. Now as I told you, we are going to generate an electrophile and we are going to use a catalyst. Here the catalyst which I am going to take is AlCl3. And now if I take AlCl3, what happens? This is aluminium, this is chlorine, this is chlorine, this is chlorine. Now what happens over here? This bond is being broken and this chlorine basically attacks on the aluminium. When it attacks on the aluminium, now this bond is broken, the electrons are moved with this chlorine and this chlorine is now electron deficient. Hence what happens over here? Cl positive is arised, and yes, this chlorine when it comes to the aluminium, what happens? It basically already had 3 chlorine with it, and 1 chlorine came over here which contained electrons with it, which contained students electron with it, which when electrons were present with it, it had a negative charge. So yes, this whole will have a negative charge over this. Now, what is the generation of electrophile over here? The electrophile is the one which is already having a positive charge and is electron loving, which loves electron. So what is electrophile over here? Cl is the electrophile over here, which itself has a positive charge. This is the electrophile. This is the electrophile in this case. Is it clear to you? Electrophile is the one which itself has a positive charge and attracts electron towards it. Next comes Friedel-Crafts alkylation. If I talk about Friedel-Crafts alkylation, again I'm going to use my catalyst AlCl3. Again I'm going to do. Now what is here reactant? The reactant which we are using is methyl chloride, that is CH3Cl. Again the same step is going to happen over here, students. Now this bond will be broken and it will attack on aluminium. The electrons chlorine takes with itself, and hence this carbon is now electron deficient, making it as CH3 positive. And here what we are going to get, Al is now making bonds with 4 chlorine atoms, and the overall charge, students, is negative over here, again negative. Now this is what? This is the generation of electrophile over here. This is the generation of electrophile. This is the first steps that we are doing in each of these reactions. In each of these reactions, this is the very first step. If I talk about the next one, that is Friedel-Crafts acylation. In acylation, students, what we are going to take over here, see very carefully. It is also the same. Okay, now check over here. It is also the same. What is going to happen over here? Again AlCl3. This bond is going to break, this chlorine is going to attack over here. What we are going to get? Generation of electrophile, and it is the same thing. Negative charge over this surface. Is it clear to you? Is it clear to you? It is quite simple, students. See here, it can also be written in this form. CH3C double bond O positive. Is it clear to you? Now this is what? This is Friedel-Crafts acylation. This is the previous one was Friedel-Crafts alkylation. This is Friedel-Crafts acylation, right? Now let us see the next case. Okay, the next case is nitration, students. Likewise, we did in the previous section, we took our reactant and we took a catalyst, and with the help of catalyst, we got our generation of electrophile. Now, in the case of nitration and sulfonation, we have already done this. The same process will occur. One single bond is going to break, and then there will be electrophile, and yes, you are going to also get one negative charge species. Students, if I talk about nitration, we are going to take HNO3. Now this is the structure, and yes, here we are not going to take AlCl3, but we are going to take H2SO4. When I'm taking H2SO4, what happens over here? The bond between this brokens up, and yes, this oxygen attacks over this hydrogen. The lone pairs attacks over here. What we are going to get? What we are going to get over here is that we are going to remove HSO4 because this bond is going to break. This portion is removed. Now what we have got? We got this. One hydrogen is now attached. This hydrogen moves to this oxygen. Now this is formed. Now what happens over here? What happens? Water molecule gets removed. This water molecules break the bond and gets removed. And yes, there is a generation of NO2 positive, which is a generation of electrophile. This is the generation for electrophile in the case of nitration. If I talk about the case of sulfonation, here I am going to take twice of H2SO4. In nitration, I took HNO3 and H2SO4. Here I am going to take twice of H2SO4. And again, the same step is going to happen. This bond is going to break and there is a removal of HSO4. This is going to remove it. This on this oxygen, this hydrogen is going to attack. Now, as it is electrophile, you know, this H positive, basically this H positive will move towards the electron and will form this. And again here, this water will come out and we are getting this generation of electrophile. This generation of electrophile. Quite easy. Now you got to know how to generate electrophile, students. Okay, now these were the first step, that was generation of electrophile. The next step that comes out to be formation of carbocation. See, we know that, kindly, you have now making this. You know how to generate this. Now, after generating, what you need to do is you need to attack this on the benzene ring, on the aromatic hydrocarbon. When you are attacking, this double bond is going to break and this electrophile is going to attack on this carbon. And when this double bond is going to break, see, if it is going to break, it is having a negative charge. When it is a negative charge, positive will come over it. It is having negative, so it will have positive because negative attracts positive. So this attacks over here. These double bonds are like this, and here is hydrogen, here is electrophile, and yes, it has a positive charge over here. This is the formation of carbocation, students. Now the next step is removal of proton. To remove the proton, now we require the byproduct that we obtain in the generation of electrophile, that was AlCl4 negative. Now for this, what is going to happen? Now for this Cl, now Cl will come, Cl negative will come, it will take hydrogen with itself. This bond is going to break and this will break over here, making a double bond over here, making a double bond over here. HCl is gone because from here, one Cl negative is going to come out. It will take hydrogen with it, forming HCl. Now it is left with AlCl3, When it goes from here, then this bond is broken over here, making a doubly bond, and this is now neutralized, and hence we are getting this as our product. Now if you know what is electrophile, kindly attach it to the benzene ring. That is your answer. Now let us see for the nitration. This is the process. What you need to do, first you will generate electrophile. What was the electrophile generated in nitration? NO2. So kindly directly attach over here NO2, because you know the product that you are obtaining in each of the cases is this only. So if you know what is electrophile, you can directly write the answer. So for this case, sulfonation, you know that SO3H was the electrophile, so directly write SO3H, right? Now for the case of halogenation, you know Cl will come. So directly Cl positive was the electrophile, so Cl will attack over here. Now for Friedel-Crafts acylation, alkylation, you know that what was the electrophile? CH3 positive, so CH3 is directly attached over here. Now for Friedel-Crafts acylation, what was the electrophile? CH3 C double bond O positive was the electrophile. So yes, CH3 C double bond O positive was there, so it is directly attached over here. Is it clear to you? Yes. So it is quite simple if you know all the mechanism in depth. So yes, my dear students, this ends our chapter of hydrocarbons. I want you all to practice DPP questions. Why? Because we have done a lot of reactions today in this lecture, one short lecture. But without practice, I would say that would be incomplete. But you need to do. If you are not doing, students, then you will be confined to a particular state of notes only. But if you will practice, if you'll put your concepts into the question, then you are going to get that, yes, I have understood the concept. So if you want to make your concept strong, listen to the video once, then read your notes. And the next step you want to do is, if you are forgetting any of the thing, if you don't know how to remember a reaction, apply it on the question section. Whenever you are doing questions, you are learning. Do not say that, no, first I will learn all the reactions and then I will apply questions. No, that learning will take a lot of time. What you have to do is you have to watch the lecture, you have to make the notes, watch the lecture once, read the notes once, and then apply the questions. And if you're not getting the questions, come back to the video lecture, listen to the lecture again, listen to read the notes again, then apply on the question. And I am telling you, I am assuring you, you will be able to do questions. And this is the best way to do any of the questions. It is the best way to learn the chapter, right? So students, I want you all to practice, because practice makes a man perfect. And yes, you can do everything, you can achieve everything if you believe on yourself. So with this note, I end this video lecture over here, and we will see you in the last chapter of organic chemistry. Thank you so much. Have a good day.